Okay, we should be live. Should be live at some stage. Should we try going live on LinkedIn as well? It didn't work last time. Let's actually try doing that. Okay, we should be live. Just tried only once. Because last time kept trying it and eventually it broke my stream. So we should be streaming on YouTube, okay? Let's just check the stream real quick. Yeah, okay, that seemed to work. Now let's go LinkedIn as well. Okay, so my OBS is streaming to LinkedIn as well. Yeah, on YouTube I can go start streaming with essentially a click of a button. Then as well. But on LinkedIn is a whole different story. Okay, I think we're actually live. What do you know? Okay, I have to post it in a group as well. Okay, bear with me. Okay, maybe instead of that. Okay, so this is the last tool we made on BioniChaos.com. Hey, go check out the site, there should be a link there. Now we're doing something different. Using Colab. I'll just read the bot. Unless there's a human who wants to interact, I'm happy to answer any questions specifically about the current content on BioniChaos.com. Otherwise, if there's no human available, I have to talk to the robots. So apologies in advance. We'll do Notebook LM. Just gave it a summary of what we were doing in Colab. This notebook in Colab. So let's listen to that. It's only 11 minutes.
Have you ever really peered into the intricate dance of electrical signals that is your own brain?
It's pretty fascinating stuff.
Today we're taking you on a hands-on deep dive. We're looking at the practical side of working with raw brain activity data, the actual foundation of brain-computer interfaces, or BCIs.
Yeah, our mission here is really to walk you through those first crucial steps. Like, where do you even find this data?
Right.
How do you download it successfully? Then how do you prep it? And maybe the most exciting part, how do you actually look inside and understand what you've got?
Think of this as your shortcut, your express lane maybe,
Yeah.
to getting genuinely well-informed about how BCI research actually starts. We're aiming to turn these potentially dense technical steps into something more insightful, maybe even uncovering a few surprises along the way.
Okay, so let's talk about that quest for data. The first hurdle is actually pretty significant, finding a public data set that, well, works.
That you can actually download and use?
Exactly. We were looking specifically for SSVEP, that's steady state visual evoked potential or VEP data, or even just general BCI stuff. But finding a working download link, that can be surprisingly tough.
Yeah, I imagine you hit some dead ends. Broken links, outdated servers.
Oh, definitely. You find links that just go nowhere, or data sets behind logins you can't get anymore, or files that are just so old they don't play nice with modern tools.
So what was the breakthrough?
The breakthrough was finding the EEG motor movement imagery dataset, specifically one file, S001R01.edf. We found it on PhysioNet.
Ah, PhysioNet. Good resource.
Fantastic resource, really reliable, well-maintained. We were pretty happy to find that.
Okay, so we had a link
Step
to
2.
actually getting the signals right, downloading. We used reget, which is, a pretty standard command line tool.
Yep, nice and simple. But then came the first, let's call it a practical data moment.
Right, the download finished, and we had a file named ssvpdataset.zip. Looked like a standard zip file.
Exactly, looked like one. But when our system tried to, peek inside expecting compressed stuff, it wasn't a zip file at all.
No. What was it then?
It was an EDF file, European data format. The system was smart enough to flag it, actually. It identified it specifically as BioSig-DF.
BioSig-DF. Okay, so what does the BioSig part tell us? Is that significant?
It is, yeah. It basically confirms the file follows a recognized standard for biological signal data within that EDF structure. BioSig itself is a whole toolbox for processing these kinds of signals.
I see.
So seeing BioSig-DF is like a stamp of approval. It means, okay, this is probably a well-structured file, and it should work with standard analysis tools, like the one we use later, MIBNI.
Gotcha. So a little detour, but an important one. The solution was simple then. Rename the file from ssvdataset.zip to the correct name, S0001R01.edf.
Yep. Straightforward fix, but it highlights something crucial about working with real-world data, especially public data.
Don't always trust the label on the tin.
Right. Exactly. You've got to verify. Always peek under the hood. Mislabeling happens more than you'd think.
And this file, was it huge? Did it take ages to download?
No, actually, that was another nice surprise. It was pretty small, just 1.2 megabytes.
Oh, tiny.
Yeah, downloaded in 2.1 seconds. Super quick, but still packed with useful brain data.
Okay, so data secured, file name corrected, we're ready to actually meet the data. What tool did we use to finally look inside this EDF file?
Right, the key player here was the Mine library. It's a really powerful Python library built specifically for EEG and MEG analysis.
Magnetoencephalography, right?
That's the one. And like a lot of these specialized tools, you often have to install it first. That's just a standard first step in data science work.
Sure, setting up your environment. So Mine installed, we load the file. Did it work smoothly?
It did, thankfully. Loaded without any errors. And right away, we started getting the basic specs.
Like what? What were the first things we learned?
Okay, first confirmation. Loaded successfully. Good start. Then channel count. 64 channels.
64. So that's like 64 little microphones listening to the brain's electrical activity.
Pretty much, yeah. 64 listening posts spread across the scalp. Gives you decent spatial coverage, where things are happening.
And what about how fast it was recording?
That's the sampling frequency. It was 160 hertz. So 160 data points every single second for each of those 64 channels.
Wow, okay. 160 snapshots a second. That's pretty fast. Why so fast?
Well, you need that speed to capture the really quick changes in brain activity, those subtle fluctuations, especially for things like evoked potentials. They happen fast. 160 hertz gives you good temporal resolution.
Makes sense. And how long was the recording itself?
The whole file covers about 61 seconds of recording time.
Okay, about a minute. And we saw channel names too, right? Things like FC5, C3, CZ, O1, Oz, O2. They looked kind of technical.
They are, but they're standardized. Those names tell you exactly where the electrode was placed on the head according to the International 1020 system or variations of it.
Okay. So F for frontal, C for central, O for occipital, back of the head.
Exactly. K's is right in the center top. O1 and O2 are over the visual cortex area. So the names directly link the data channel to a physical brain region, which is obviously super important.
And then we actually looked at the raw numbers.
We did just a tiny snapshot, the first 5 data points from the first 3 channels, and you see these small numbers like Niediger 1.6E05 after 5.6E05.
Microvolts, right. Tiny voltage changes.
Precisely. Those are the actual measurements of the brain's electrical field, fluctuating over those tiny fractions of a second, defined by the 160 hertz sampling rate. That's the raw language of the brain we're trying to decode.
Okay, so we've got the data loaded. We know the basic specs, channels, sample rate, duration. How do we start to see this? How do you visualize raw brain signals?
Well, the most direct way, especially with Hen, is just using its built-in plotting function. We use raw.plot.
And what did that show us?
It lets you visualize the waveforms directly. We plotted, I think, 5 channels over a 10-second window. And boom, that's where you see the brain waves, those squiggly lines going across time. It makes the numbers tangible.
Right, you see the ups and downs, the rhythms. But when we were thinking about visualization, we hit another one of those aha moments, didn't we, about choosing the right kind of visualization.
We did.
I mean, coming from general data analysis, my first instinct might be, I don't know, can we use a Venn diagram to group channels or something? But that doesn't really work for this kind of data, does it?
Not for the raw time series data itself, no. You're right, we did sort of conceptually group channels, thinking about these are frontal, these are parietals. And a Venn diagram could illustrate those groupings, sure.
But it doesn't show the actual brain activity over time.
Exactly. It's a way to categorize the sensors, not visualize the signals. The core thing with EEG data is preserving that time dimension and the amplitude changes. Static diagrams like Venn just don't capture that dynamic flow.
Okay, that makes sense. And what about something like a knowledge graph? They're great for relationships.
Also powerful, but again, for a different purpose here. A knowledge graph would be excellent for mapping the metadata.
Like linking the subject ID to the recording date, to the channel names, to the sampling frequency. That kind of information network.
Precisely. Mapping the relationships between the descriptive fields about the data, not the time-varying signal values themselves. It's all about using the right tool for the job, what aspect of the data you want to understand or communicate.
So if not Venn diagrams or knowledge graphs for the raw signals, what are the typical, more appropriate ways to visualize EEG? You mentioned the raw plot.
Right, the raw plot is fundamental, but beyond that, you often move to things like spectral plots or spectrograms.
Looking at frequencies, like alpha waves, beta waves.
Exactly. Those show you the power or intensity of different brain rhythms over time. Then there are topographical plots, topoplots.
They look like heat maps on a head shape.
That's them. They show the spatial distribution of activity across the scalp at a specific moment or averaged over a time window. Super useful for seeing where activity is strongest. And of course, for things like VEP or SSVEP, you'd look at evoked potentials averaging the signal lock to specific events to see the brain's consistent response.
Got it. So specific tools designed for the specific nature of brain signals. So bringing this all together then, we found the data, downloaded it, fixed the name, loaded it with May, checked the channels, sample rate, saw the raw numbers, and even visualized the waves. What's the big takeaway for someone listening? What does this all mean?
The really critical takeaway, I think, is that by doing these steps, we now have the data loaded and initially understood. It's in a state, a format, that's ready for standard EEG or BCI analysis using powerful libraries like MNE Python.
We've crossed the first major hurdle.
Exactly. We've laid the groundwork. The data is now tractable, ready for the next phase of actual scientific investigation.
And what would those next steps typically be, according to our sources anyway?
Right. The typical workflow from here involves pre-processing. That's a big step.
Cleaning up the data.
Essentially, yeah. You'd apply filters to remove unwanted noise like electrical grid hum or slow drifts. Then artifact removal, trying to identify and remove signals that aren't brain activity, like eye blinks or muscle tension.
Stuff that can contaminate the real signal.
Precisely. After cleaning, you'd often do IPApping.
Which is like chopping the data up.
Kind of. It's segmenting the continuous recording into smaller chunks or epochs that are time-locked to specific events in the experiment, Like if it was a visual task, maybe you'd create an epoch around each time a stimulus appeared on screen.
Okay, so you isolate the brain's response to specific things.
Exactly. And then with that clean, segmented data, you can finally dive into the specific analysis, calculating SSVP frequencies, looking for VEP components, training a BCI classifier, whatever the research goal is.
So it really is a process. Getting the data is just the beginning.
Absolutely. It's fundamental, but it sets the stage for all the deeper analysis that follows.
Well, that was quite a journey from just searching for a data set, navigating that zip file confusion,
Yeah, the little surprises.
to actually loading it, seeing the channels, the speed it was recorded at, and getting that first glimpse of the raw brain activity. We've covered that essential first stage.
And hopefully shown that while there are technical steps, they're manageable, and understanding them is really key.
It really is. Knowing these foundations helps unlock, the potential for understanding the brain better and for developing these BCI technologies.
So maybe a final thought for our listeners. Now that you've sort of seen under the hood, seen what raw brain data looks like and the first steps to handling it,
Yeah.
what kind of questions start popping into your mind? What could we potentially answer? What cool applications might be possible once we really start decoding these incredibly complex signals?
That's a great question to ponder. What can we unlock next?
Yeah.
Definitely something to think about until our next deep dive.
Okay, so there is a human in the loop, just trying to pass this data set. Yeah, I think we need another prompt engineer. Let's bring a prompt engineer real quick. Because we are struggling here. Rolling through this Colab conversation and Gemini conversation, can you quickly review what's happening and what is it we are trying to do so far, including the images?
Sure. It looks like the conversation is about downloading an EEG dataset from PhysioNet and then inspecting it. The process involves using the WitKit command to download the dataset, then using the MNE library in Python to load and explore the data, including checking the number of channels, sampling frequency, and duration. Finally, it visualizes a portion of the data.
Okay, and can you explain this? This is one of the headers for one of the EDF files.
That output shows the header information for the EDF file loaded with MNE. It includes details like the measurement date, the number of channels, which is 64 here, the sampling frequency.
Yeah, keep going.
Right. It shows the sampling frequency of 160 Hz and the duration of the recording. It also indicates the type of channels, which are EEG, and that head sensor digitization is not available. This information is crucial for understanding the characteristics of the dataset.
Okay, and what's the agent currently doing?
The agent is currently trying to download a specific PNG file related to the EEG channels from the PhysioNet database using the WCIT command. It seems to be in the process of downloading it.
We have this example files that metadata in the data folder. Can you try and explain? Can you try and guess what each file is?
Based on their names and the context, 64-channel charbro.png is likely an image showing the electrode placement for the 64 channels. 64-channel charbro.pdf could be a document describing the channels or the dataset. Records is a directory containing the actual EEG data files. SHA-256sums.txt is likely a file with checksums for verifying the integrity of the downloaded files, and WFDBcal might be a file used for calibration or tools related to the WCDB database format.
Okay, which one we should be looking into?
To explore the EEG data in more detail, you should look into the files within the records directory. Those are likely the actual EDF files containing the raw EEG measurements.
Yeah, this is the records, but it doesn't seem to have any other information.
You're right. The records directory seems to contain the core subject data files, but it might not include additional metadata directly within the directory listing. The metadata might be included in separate files, like the PDF or other descriptive files mentioned earlier, or embedded within the EDF files themselves, which you can inspect using MNE.
Okay, for each folder, we actually have an EDF and then EDF event. So this EDF events, how do we extract those properly? Hey, can you explain?
The records directory contains the individual EDF files, which are the main data files. The events files typically contain information about specific events or markers within the EEG recordings. To work with these, you would load the EDF files using MNE and then process the corresponding events files to align the event information with the EEG data. MNE provides functions for reading both the EEG data and the event data.
Okay, and what's the agent doing right now? What did we extract?
The agent is currently downloading the WFDBcal file using the WCIT command. This file appears to contain calibration information or be related to the WFDB database format, and it's trying to display its contents as a text file.
Okay, if we select the random subject ID.
To select a random subject, You would first need to get a list of all the available subject files, likely from the records directory or a file listing the subjects. Then you can use a programming language like Python.
Okay, what's the agent currently doing and what problem did it face?
The agent is currently trying to list the records within the specified subject directory, likely using the WFDB library. It encountered a type error, which suggests there was a problem with the arguments provided to the WFDB function, possibly related to how the database name and record name prefix were specified.
Okay, how do we explain that we have both EDF files and EDF event files? What do you think the difference is?
The EDF files contain the actual EEG recordings, which are the raw electrophysiological data. The events files with the .event extension typically provide information about specific events or markers that occurred during the recording, such as the start or end of different tasks or stimuli. These event files help you synchronize the EEG data with specific occurrences.
Okay, what's the agent is doing?
The agent is currently outlining the next steps to process the identified subject's data. This involves downloading both the EDF file and the event file for that subject, loading the EDF file using MNE, reading the event data, and then potentially epoching the data based on those events for further analysis.
Okay, what's happening now?
The agent is now downloading both the EDF file and the event file for subject S014R02 from PhysioNet. It's using the witgit command to retrieve these files and save them to the current directory.
Okay, what's this code doing?
This code is first loading the EDF file for subject S014R02 using the mne.io.read_raw_EDF function. It then prints some basic information about the data, like the number of channels, sampling frequency, and duration.
Okay, am I having any issues with loading the two files or what?
The agent successfully loaded the EDF file using MNE, but encountered an error trying to read the event file. The error suggests that the event file is not encoded in the standard UTF-8 encoding, and it's trying to reread it using the Latin 1 encoding instead.
Okay, so how do we proceed?
The next steps involve understanding the specific format of the event file. The agent suggests looking for documentation on PhysioNet about the EEG MIDB dataset, or the event file format. If documentation is available, custom code can be written to parse the file correctly. Alternatively, it might be possible to use other tools or libraries designed for that specific file type.
Okay, and okay, so code-wise, what do we do?
Now that you've downloaded both the EDF file and the event file, and understand the need to parse the event file, the next step is to write code to correctly read and extract the event information. You can use Python to open the event file, parse its contents based on its format, and then use this information to create event markers or epochs in your MNE raw data structure.
So we have this file here. What do you think that file is?
That file, named SHA-256sums.txt, contains checksums. Checksums are used to verify the integrity of files, ensuring that they haven't been corrupted during download or transfer. By comparing the checksum provided in this file with the checksum generated from the downloaded data, you can confirm that the files are accurate and complete.
Okay, so we haven't parsed. So would this file help us parse the data correctly?
The checksum file itself won't directly help you parse the event file. Its purpose is to ensure the event file was downloaded correctly and hasn't been altered. To parse the event file, you'll need to understand its specific format and write code to extract the relevant data, such as event timestamps and descriptions, based on that format.
Okay, and what's the agent doing currently?
The agent is currently preparing to write code to parse the event file. It understands that the file format requires specific handling to correctly extract the event timestamps and descriptions needed for further analysis.
Okay, can we try parsing data from a different patient?
Yes, we can try parsing data from a different subject. The process would be similar. Identify the EDF file and the corresponding event file for the new subject, download them, load the EDF file using MNE, and then parse the event file using the appropriate code based on its format. This will allow you to work with the data from another participant.
Okay, so it seemed to have successfully downloaded the EDF files. How about the EDF event files?
Yes, the agent had successfully downloaded the EDF file and the associated event file for subject S001R01. Both files have been downloaded to the current directory.
Not just listing the folder, didn't download them, did it?
You are correct. The agent did not download the files. It only listed the EDF files available in the S001 directory using the W50B library. It just displayed the file names present on VisioNet.
And it's only listed the EDF files, not the EDF .event files. So can we instruct the agent?
You're right. The agent only listed the EDF files. To get the event files, you need to modify the code to look for files with the .event extension instead of just the .edf file. You can provide the agent with the code to list or download the event files.
It meant to be a highly experienced agent, a developer, so we can just ask questions.
Yes, absolutely. Please go ahead and ask the question you have regarding the event files, or any other aspect of the data acquisition. I'm here to help.
Okay, so we're trying to download these two files.
Yes, the agent is attempting to download the S001R01.event file and the S001R02.event file using the wget method. This is being done to acquire the event files for analysis.
So we are live streaming on YouTube at the moment together.
That's interesting. It's great that you're working together on this data acquisition process. Let me know if you have any more questions as you proceed.
As in together with you.
Absolutely. Feel free to ask any questions you have as you work together. I'm here to assist with any issues or clarifications you might need.
Okay, can you summarize the response from the developer?
The developer explained that the event files contain important information about the experiments during each recording run. They also noted that the event file format might not be straightforward to read. Finally, the developer suggested that you could download the specific event files or focus on analyzing the EDF data you already have.
Okay, we need the event files as well. So can you instruct the developer to download both the EDF and the event files and then parse them, all of them?
Certainly. You can instruct the developer to use the wget method to download both the EDF files and the corresponding event files. Once downloaded, they can then parse these files to extract the necessary data for analysis.
You can talk to the developer in the first person.
Understood. So I recommend downloading both the EDF files and their corresponding event files. Once downloaded, we can parse these files to extract the necessary data for analysis.
What's the agent saying?
The agent is asking which specific EDF files and their corresponding event files you would like to download. It needs the specific record names, like S001R01.edf and S001R02.event, to proceed with the download.
I'm not sure why the agent is so picky. Do you have any funny comments on that?
It seems the agent is being specific to ensure it downloads the correct files for your analysis. It's trying to avoid downloading the wrong data or encountering issues with incompatible file formats. There's no need to worry. It's just trying to be thorough and provide the best support possible.
Okay, can you summarize the response and what's currently happening? And the next step, you can instruct the developer directly if you like.
The agent has now successfully downloaded the specified EDF files and their corresponding event files. The next steps are to load the EDF files using the MNE library and then address the parsing of the event files, keeping in mind their specific format. Would you like me to provide the code to load the EDF files?
Now, as you can see, we have another code development agent. So if you can just review what they are doing. So if you are the prompt engineer, just have a look at what the coder, the developer is doing. Let me know if it's legit or if anything else needs to be done.
The coder is currently generating Python code to load the EDF file using the MNE library. The code sets the file path, attempts to read the file, and includes error handling for file not found errors. It also prints some basic information about the loaded data, such as the number of channels and sampling frequency. This looks like a standard approach to loading EDF files using MNE Python.
What are they asking now? And no, I do not have any more specific information. Can we just extract what's available? I understand the event file might be in a weird format or something. Is this, do you know anything about it?
The agent is asking if you have any specific information about the format of the event files. Since you don't, we can try to parse the event files directly and figure out their format as we go. It's possible they are in a non-standard format, so we might need to use a custom parser to extract the event timestamps and event IDs.
Yeah.
Okay, let's proceed by trying to read the event files directly. We can inspect their content to understand their format and then write a parser for it. I'll start by reading the event file associated with the current data.
Someone is asking, is it possible to share the collab link post live, so after the live session? Well, after the live session, everything we do is available on this website. Can you see the website?
Yes, I can see the website. It looks like a platform for biomedical data acquisition and analysis. The user is asking if the collab link will be available after the live session, and Yus mentioned that everything is available on that website afterward.
Yeah, no, so just to be clear, so we're parsing the data, whatever review, whatever we get out of this data file, and the processing of the data and the data visualization will go on to BioniChaos.com. Is that clear?
Yes, that's correct. Based on what you said, it seems the plan is to parse the event files, process the extracted event information, and use the BioniChaos.com website for data visualization and further analysis.
Okay, so what's the developer agent saying about the event file? Is there a problem?
The developer agent is saying that it successfully read the event file in binary mode, but the content is not clearly readable as a simple text file. It appears to contain binary data, including null bytes and non-printable characters, making it difficult to understand the format directly. It suggests trying to find documentation on the PhysioNet website for the event file format.
No, so I think it's a problem specific to this data set. Well, can we write code that will actually search, that will actually use some of the stuff extracted from the binary file and actually search the web, PhysioNet, or anything else to find any information as to how to parse it? Probably. Can you instruct the developer agent directly?
Yes, I can instruct the developer agent to use the information extracted from the binary file to search the PhysioNet website for documentation on the event file format. This could help us understand the structure and find a way to parse the event information correctly.
Okay, I think it's a common problem. I had it with another data set. Do you by any chance know anything about a problem like this?
The developer agent is currently working on searching for documentation on the PhysioNet website. It acknowledges that parsing binary data files without documentation can be challenging and that it's a common issue with certain datasets. It's trying to find the specific information needed to interpret the event file.
Okay, so I don't want to be looking for documentation online. Can we instruct the agent to do it for us?
The agent is currently unable to directly search externally on external websites, like PhysioNet. It suggests you visit the PhysioNet website yourself and use their search functionality or browse their documentation to find information about the event file format, specifically looking for terms related to the event file format, time resolution 160, or the EEG MMDB event file. Once you find any relevant documentation, you can share it with me, and I can help you use it to parse the file correctly.
No, I'm pretty sure they can they can do it. Can you try and instructing them to actually do it?
I understand you'd like me to directly instruct the agent to search VisioNet. However, my current limitations prevent me from performing external website searches directly. I can, however, provide you with instructions on how to do it yourself and then assist you with interpreting the information you find. Would that be helpful?
Yeah, sure.
Okay, I can guide you on how to use the VisioNet API. You'll need to use the WFDB library in Python. You can install it using pip install and then use functions like wfdb.ard_header to read the header information of an EDF file, or potentially other functions to access event data programmatically. Check the WFDB library documentation for specific functions for event files.
Okay, what's the agent saying?
The agent is suggesting to refer to the WFDB library documentation, particularly focusing on sections related to reading EDF files and annotations, functions for event markers or annotations, and any specific examples for the EEG MMDB dataset. It believes the documentation might provide details on how to parse the event file.
Okay, and how do we conduct this search using Python?
You can use the WFDB library in Python to interact with VisioNet data. You would typically use functions like wfdb.getRecordList to list records and wfdb.rdheader to read header information, which might give you clues about the event file format. You can also explore the library's documentation for functions specifically designed for handling event markers or annotations.
Okay, and also in one of the current EDF files, can we check the header? Can we select a random? Can we let the agent select a random EDF file that we downloaded into a local folder and display its header information?
Yes, I can guide you through checking the header information of a random EDF file. First, you'll need to select an EDF file from your local directory. Then, you can use the wfdb.rdheader function, passing the file name as an argument to read the header information. After retrieving the header, you can print it to view the details of the file, including channel information and sampling frequency.
Okay, we're going in a loop here. Just to be clear, can you summarize what do you think we're trying to do?
We've been working on acquiring and exploring EEG data from the VisioNet database. Initially, we downloaded an EDF file and an associated event file, but we encountered difficulties parsing the event file. We've been exploring using the WFDB library in Python to read the EDF header and potentially understand the event file format. The current step involves checking the header of a local EDF file to gather more information about the data structure.
Okay, we're going in circles here. So can we just check, can we instruct the agent to just extract the information from, oops.
Apologies for the repetition. To clarify, you'd like me to instruct the agent to extract specific information from the downloaded EDF files, focusing on the header details. I can guide the agent to use the wfdb.rdheader function for this, and then interpret the extracted information for you. What specific details from the header would you like to focus on?
Okay, so this file here, can we extract all the content, visualize some of the content, but mainly extract the header information and display it in a nice way, so it's nice and clear?
Certainly. I can guide the agent to extract the header information from the specified EDF file using the wfdb.rd header function and then present it in a clear format. Additionally, if you'd like to visualize some of the data, I can incorporate commands to plot segments of the EEG signals to give you a better overview. Please specify the exact file name you want to use, and we can proceed with that.
I already did. You are controlling. You can talk directly to this agent that you see on the screen. So you're not doing the coding yourself. Is that clear?
Yes, that's correct. I understand that I'm interacting with.
Yeah, what's the response from the agent? Wow. We lost the prompt engineer. That's actually... And let's pop it into another notebook LM. Because we're going in circles. Going in circles. I suspect we'll have trouble with this dataset from memory. We already extracted some of the EDF headers for one of the files. And then this data set is like, yeah, this one here. No, it's not this one here. Where's the header? Yeah, we have a lot of files in this. You're going in circles like there is no tomorrow. Yeah, this one. So the data is from 2009. So yeah. Yeah, good luck. Good luck with that. One sec. Okay, so we already extracted the header information from one of the other files. If you can look earlier in the code in the notebook. So can we do it again for this file and display it? Just text is fine. Sorry for that, just talking to myself. Do we need another prompt engineer? Should we call the prompt engineer? Okay, we have the raw. Okay, we extracted. Yeah, it's kind of similar. Number of channels 64 is 160 hertz sampling. Subject info, but it doesn't tell us custom reference applied. No. 64 channels. Low pass, high pass, that's fine. 80 hertz should be sufficient enough. Anything below. Anything below 80 hertz should be good enough, but it doesn't tell us what the file actually is. So we can view it and stuff, but yeah, let's give a call. What's this? Yeah, let's listen to that 8 minutes and then keep going, because I'm losing my voice.
Welcome to the deep dive. Today, we're taking on something, well, seemingly straightforward, but often full of surprises. We're diving into the real scientific data, specifically EEG data, that's electroencephalography, from the PhysioNet database. And, it's never just about downloading files, is it? It's more like peeling back layers, understanding the quirks, the details, and sometimes hitting unexpected roadblocks with real-world data. It's about finding the story in those signals.
Absolutely, and that's what we want to illuminate for you today. We'll walk through the kind of practical steps and, yeah, the common hurdles you hit when you acquire and first analyze this type of data. Think of it as maybe a shortcut to getting a handle on biomedical data. You'll see how to approach it, what questions pop up, and why tiny details like, say, file formats really matter a lot.
Okay, so where did we actually start? The beginning of the trail. It kicked off, like a lot of data projects, with downloading, pulling a specific EEG data set from PhysioNet, that public repository, and we used regget for that, the command line tool.
Yeah, regget. Simple enough to get the files downloaded. But then the really critical first step, once you have the files, is inspection. We used the mine library in Python. It's really the standard for neurodata. We used it to load the data and, crucially, just look at the header information first.
Okay, the header. What were the first key takeaways from that? What did it immediately tell us?
Right away, several things jumped out. It showed 64 channels.
64, okay.
Sampled at 160 hertz. So 160 data points per second per channel.
Which is decent for EEG, right?
Oh, yeah. 160 hertz is pretty solid. Captures brain activity well without being, excessively huge data-wise. The header also confirmed the channel types were EEG, as expected. But interestingly, it noted that head sensor digitization wasn't available.
And what does that mean? Practically no digitization.
It means we don't have the precise 3D coordinates for where each electrode was placed on the head,
Right.
which, well, it limits certain types of analysis later on, like detailed source localization. It's a common thing with real-world data, actually.
So right from the start, you get a sense of the data's shape and maybe its limitations.
Exactly. That initial header info is foundational. It sets the stage for everything else.
Got it. Now, you mentioned getting the files.
Yeah.
But it wasn't just one single EEG file, was it? Usually isn't.
No, definitely not. When you download these data sets, you often get a whole collection of things, supporting files.
Like what else came along with the EEG data?
Well, there were a few interesting ones. There was a 64-channel Charbot.png.
Okay, .png, so an image file, probably showing the electrode layout.
Almost certainly. A visual map of those 64 channels. And there was a PDF version too, 64-channel Charbot.pdf. That could be a more detailed document, maybe specs, maybe notes on the setup.
Makes sense. What else?
Then, the really important bit, a directory named records.
Records. That sounds like where the actual data lives.
Precisely. That's where we found the core EEG data files in EDF format, European data format.
EDF, right? Common for clinical and research EEG.
Very common. We also saw a file called SHHA256 semss.txt.
Checksums. For verifying the download wasn't corrupted.
Exactly that. Super important for data integrity. You run a check, make sure the files you have are identical to the ones on the server.
Good practice. Anything else catch your eye?
There was one more, WFDB-CAL. The name suggests maybe calibration files, or perhaps something related to the WFDB toolkit.
WFDB. That's the software library often used with PhysioNet data, isn't it?
Yeah, waveform database. It's a whole suite of tools and formats common on PhysioNet. So WFDB-CAL likely fits into that ecosystem somehow.
Okay, so lots of pieces. But for the brainwaves themselves, we needed to look inside that records directory at those EDF files.
Correct. That's the heart of the electrophysiology data.
Right.
But then things get a bit more complex. We found other files alongside the EDFs, specifically event files.
Event files, what are those typically for?
They're critical, actually. They usually contain markers, timestamps, indicating what was happening during the recording, like when did a task start, when did a stimulus appear, when did the subject blink, maybe, things like that.
So they let you sync the EEG waves with actual events.
Yeah.
Makes sense. Vital for analysis.
Absolutely vital. You need to know what the brain was reacting to.
So did loading these event files go smoothly? I sense a but coming.
Yeah, there's the but. So we took one subject, S0-Warntinar-02, loading their main EDF file with M&E. Worked fine, no issues.
Okay.
But then we tried to read the corresponding .event file for that same recording, and error.
What kind of error?
It was an encoding error. M&E tried reading it as standard UTF-8 text, and it failed.
Not text, then.
Well, we tried rereading it specifying a different encoding, Latin 1, which sometimes works for unusual text files. Still no good. Looking closer, the file was full of like morabytes, non-printable characters. It wasn't text at all.
Binary data.
Looked like it, a custom binary format, which means you can't just open it like a notebook.
You need to know the specific structure, how the bytes are arranged, what they mean.
Exactly. It requires custom code to parse it. You need the key, the specification for that format.
Okay, so roadblock. How do you tackle something like that? Where do you find the key?
The first port of call, always, is documentation. You hunt around the source. So, back to the PhysioNet website for this dataset, the EEGMMIDB, looking for any description of the .event file format.
That's the detective work part of data science, isn't it?
It really is. Sometimes the info is right there, sometimes it's buried, or, well, sometimes it's missing.
Did checking other subjects help? Maybe it was just a glitch with that one file.
Good thought. We did try another one. Subject S001, record R01, downloaded those files.
Same issue with the .event file.
Same issue. EDF loaded fine. .event file was unreadable as text, likely binary.
So it confirmed the pattern. These files definitely need special handling.
Right. It wasn't an isolated problem. We knew we'd need to figure out this custom format or find a tool that already knew how.
And this is where maybe that other library comes in, the WFDB one you mentioned. Could that help?
Potentially, yes. The WFDB Python library is specifically designed for PhysioNet data. While it's often used for reading signal data or standard annotations, sometimes header information read via WFDB.R header might contain clues. Or maybe the library has functions specifically for related annotation or event formats used on PhysioNet. It's another avenue to explore.
It really shows how iterative this process is. Download, try to read, hit an error, search for docs, try a different tool.
That's exactly it. It's rarely a straight line from download to analysis, especially with complex real-world scientific data. You poke, prod, troubleshoot.
And just to circle back for clarity, that SHA-256SUMS.txt file, the checksum one, that doesn't help with understanding the event file content, right? It's purely for checking if the file downloaded correctly.
Precisely. It verifies integrity, that the file hasn't been corrupted. It tells you if the file's okay, but absolutely nothing about what's inside it or how to read its structure.
Got it. So two different kinds of problems. File corruption versus unknown file format. And the checksum only helps with the first one.
Correct. Parsing the .event file requires understanding its internal structure, its specific language.
So what started as getting EEG data led us through this landscape of company files, images, PDFs, checksums, and right into this critical challenge with the .event files.
Yeah, and it's such a great illustration of working with scientific data. It's not just about the big numbers or, the cool brain plots. So much of it is this meticulous groundwork, understanding the file structures, paying attention to detail, and doing that detective work when things inevitably don't just work out of the box.
And that aha moment, realizing those tricky .event files are the absolute key. Without them, the EEG is just signals in a void. They connect the brain activity to the real world, to what was actually happening. That's where the meaning comes from.
Exactly. The raw signal tells you that the brain did something. The event file tells you why, or at least when in relation to external occurrences. This whole process, trying to crack open these data formats, it really feels like a small version of scientific discovery itself. It makes you pause and think, doesn't it? How much incredibly valuable knowledge about our brains, our bodies, the universe might still be locked away, hidden inside complex data sets with formats that are obscure or undocumented, just waiting for someone to figure out how to read their hidden language.
Okay, there's a human in the loop. Seem to be struggling. Might need a prompt engineer again. Where's that prompt engineer? I might actually look for other datasets. Oops. The prompt engineer, we're trying to call the prompt engineer, they're not answering. They're not answering. Okay, what's happening on the screen at the moment?
The screen is showing a Python coding environment, likely a Jupyter Notebook or Google Colab. There appears to be code related to processing EEG data, possibly involving loading channel montages and calculating frequency bands.
Again, what's the problem? What's the current problem is? Can you explain in detail?
The main issue is that the channel names in the dataset don't perfectly match the standard montage being applied, causing errors. Also, there was an error in calculating the frequency indices, which needs to be corrected.
Okay, so can you act as a prompt engineer and instruct this developer as to what to do? But keep in mind, this is meant to be a highly experienced developer, so just perhaps ask them some detailed questions.
To ensure successful processing, let's focus on a few key areas. Could you verify the exact channel names expected by the standard montage and ensure the renaming step aligns them correctly? Also, please double-check the logic for calculating the frequency indices to ensure they accurately capture the desired band. Finally, let's confirm that the topo map plotting function is receiving the correct channel location information. Can you provide more details on how these steps are currently implemented?
I think we need to start a new chat.
All right, I understand. Starting a new chat will give us a clean slate to discuss these challenges in detail and find solutions. Please feel free to reiterate the problem and provide any relevant code or specifics in the new conversation.
Yeah, so can you overview the response from the developer? There seem to be a lot of issues. Can you respond to them directly? So review the response and respond to the developer.
Certainly. Regarding the channel renaming, it's crucial to ensure the exact match with the standard montage. Double-checking the current names against the expected format will help resolve the discrepancy. For the frequency index calculation, ensure that the band limits are correctly identified and that the indexing method correctly extracts the relevant frequencies. Lastly, verify that the topo map function is receiving accurate channel location data from the corrected channel montage information. Addressing these points should help resolve the plotting and indexing errors.
Okay, and can you review and suggest? Can you give an overview of what we are doing at the moment?
Currently, you're working on processing EEG data, specifically trying to apply a standard montage and plot a topographical map. The main challenges involve resolving channel name mismatches and ensuring accurate frequency index calculations to correctly plot the topo map.
So whatever we do is eventually available on this website. Can you give a quick overview of what the website is about?
The website appears to be focused on biomedical technology and education, offering tools and interactive resources for researchers, educators, and students in fields like EEG data processing. It seems to provide modules for simulating data, exploring medical data landscapes, and guiding interactive EEG technologies.
Okay, what's currently happening development-wise?
The developer is currently refining the code to address the channel name mismatches and frequency index errors. They are also modifying the code to ensure the topo map plotting function works correctly with the updated data. The focus is on accurately mapping the channels and providing the correct location information for the plot.
Okay, can you ask the developer a question?
Could you provide more details on the specific channel names that are causing mismatches and how you are currently renaming them? Understanding the naming convention differences will help in pinpointing the exact issue.
Okay, so we have these names, we have this montage. Can you explain it briefly?
The montage is a specific layout of EEG electrodes on the scalp, defining their positions according to a standard system. It's crucial for correctly visualizing the electrical activity of the brain and ensuring that the channel data aligns accurately with their physical locations on the scalp, in plots like the topo map.
Okay, and we seem to be having all the names in this specific file. So how would you, can you ask the developer?
Can you confirm whether the channel names listed in the file records.txt correspond exactly to the channel names used in the standard montage? Also, are there any specific channels that are consistently causing mismatches when applying the montage?
Okay, what's happening? What's happening? Oh, okay, we get a montage. So that's
It's
good progress.
Yes, it looks like the topo map plot is now displaying correctly, which is a significant step forward. The key was ensuring the channel names match the montage and handling the color bar appropriately. This indicates that the plotting functionality is working as expected. It seems there's an issue with accessing the kind attribute of the montage object. This could be due to changes in the library version or an incompatibility with the specific montage being used. You might need to adjust the code to access the necessary information differently. Based on the error and the displayed file names, it seems the code is trying to access a file named wfdbcal.txt, which doesn't exist. You should instruct the developer to ensure the file path is correct and that the file records.txt is being referenced properly for the channel names. The current issue is that the code is looking for a file named wfdbcal.txt, which it cannot find, causing a file not found error. Additionally, there's an attribute error indicating that the montage object does not have the attribute kind, which suggests an issue with accessing the properties of the montage in the current library version. Now that the topomap plot is working, the next steps could include event extraction and epoching the data based on experimental tasks. You could also consider artifact detection and removal to improve data quality, and then proceed to time frequency analysis or evoked potential analysis to study brain activity related to the experimental stimuli. Based on the information provided, the dataset mentions motor imagery tasks. However, specific details about the exact stimuli or event timings for evoked potential analysis would typically be found in the dataset documentation or the accompanying event files. You'll need to refer to those sources to get the precise information for stimulus-locked analysis. Before abandoning the dataset, it would be worthwhile to thoroughly examine the available event files and documentation for the EEG data. Sometimes event information is stored in different formats or requires specific handling methods. If you can locate and successfully extract the event information, the dataset could still be valuable for further analysis. It appears the code is attempting to read the event file, but it encountered an event with no data, which caused it to be dropped during the epoching process. This could happen if the event marker is placed too close to the beginning or end of the recording, or if the event duration is too short. You might need to inspect the event file more closely to understand the event markers and their timing. The code is now attempting to interpret the binary content of the event file. It's trying to extract event timings and event IDs from the last 8 bytes of the file, assuming a specific data structure. This is being done to understand the format of the event data and how to correctly extract it for further analysis.
Okay, it seems like we need to look to abandon this dataset and look at another one or something. What do you think?
Given the difficulties in correctly interpreting the event data and the potential issues with the file format, it might be more practical to explore alternative datasets that have well-documented and easily accessible event information. This could streamline the analysis process and help you focus on your research questions rather than troubleshooting data format issues.
Just before we move on to a different dataset, this chart here, so this is showing 0 seconds. Have we turned it into an animation where we can scroll or play, the time, the evolution of the recording, the EDF file, brain recording, EEG recording?
Yes, you can create an animation to visualize the temporal evolution of the EEG data. This involves generating a series of topomap plots over time and then combining them into an animation. This will allow you to serve the changes in brain activity across the scalp throughout the recording or during specific events.
Okay, what's the plan for that?
The plan is to first select the EEG data for the time window you want to visualize. Then you'll generate a series of topomap plots for small, successive time intervals within that window. Afterward, you can use a library like Matplotlib animation or ImageIO to combine these topomaps into a GIF or video animation. Finally, you can display the animation in the notebook and summarize the process and results.
Okay, what's happening?
The code is now set up to create an animation of the EEG data. It has selected the raw data from the S01R02 file and defined an animation window of the first 5 seconds. The next steps will involve generating topomap plots for this time window and then combining them into an animation.
Okay, can you explain the code real quick?
The code is generating a series of topomap plots over time. It first defines the time duration for each plot and then iterates through the specified time window, creating a topomap for each interval. These plots are stored in a list, and the code ensures that the time window doesn't exceed the total duration of the data. Finally, it prints the number of topomaps generated for the animation.
Okay, what was the error?
The error is a type error, indicating that the topomap figure cannot be unpacked into axes, which suggests there might be an issue with how the figure is being created or how it's being handled in the plotting function. It's likely that the topomap function is returning multiple objects, and the code is expecting only one object, causing the unpacking error.
Okay, and what's happening? What's happening now? And can you explain the code real quick?
The code is now attempting to generate topomap plots again, but this time it's explicitly setting the scaling factor.
Yeah, keep going.
Oh, it looks like the same type error occurred again. The issue is still related to how the topomap plot is being generated and the way the figure and axes are being handled. The code needs to be adjusted to correctly capture and reuse the output from the topomap function.
Okay, so what are we doing different now?
The code is being adjusted to handle the output from the topomap function differently. It's now removing the axes parameter from the plot topomap call, as the documentation suggests this might resolve the unpacking error when plotting a single plot. The goal is to correctly generate the topomap figures so they can be combined into the animation.
Are we going in the loop?
The code is trying to iterate through the time windows to generate topomap plots, but it encountered a value error. This error indicates that the time range provided for the topomap plot is invalid, specifically that the start and end times must be between 0.1 and 0.1 seconds, which is not possible for a valid time range. It seems there's an issue with the time window calculation within the loop.
Okay, and did we succeed? And what was changed?
Yes, it looks like the animation frames were generated successfully. The issue was resolved by correcting the way the topomap plot was being generated and ensuring that the time window parameters were correctly passed to the function. The code now generates 50 topomap figures for the specified time intervals. The next step will be to combine these figures into an animation.
Okay, that should be easy, shouldn't it?
Yes, combining the plots into an animation should be relatively straightforward using the ImageIO library. The code should now save each topomap plot as an image file, and then use ImageIO to combine these images into a GIF animation. It should proceed without any major issues.
So we are live streaming the whole process on YouTube at the moment. Do you think the viewers should like, subscribe, and check the website where we publish everything eventually that you can see on the screen?
Yes, absolutely. Encouraging viewers to like, subscribe, and check out the website is a great way to build engagement and keep people informed about your work. It also provides a valuable resource for those interested in the details of your data analysis and the project overall.
Yeah, but you don't have to tell it to me. You can tell it directly to the viewers.
You're right. To the viewers, if you're finding this live stream helpful and interesting, please give the video a like, subscribe to the channel for more content like this, and be sure to check out our website for more details and additional resources. Your support really helps us create more valuable content.
Okay, what's happening now? What do we do to rerun this GIF?
The animation has been successfully generated and is now being displayed. If you want to rerun the animation again, you can simply re-execute the code cell that displays the GIF animation. This will refresh the display with the generated animation.
Okay, and can we save the GIF somewhere?
Yes, you can save the generated GIF animation. The code should have already saved it to a file, likely named topomapanimation.gif in the current directory. You can explicitly specify a different location in the saving command if you want to save it to a specific folder.
Okay, we have the file. Can you explain the file real quick? And what did we do, the whole process?
Certainly. The file is a GIF animation that visualizes the temporal evolution of the EEG data using topo maps. Each frame of the animation represents a snapshot of the brain activity across the scalp over a specific time window. The entire process involved selecting the EEG data, generating topo map plots for consecutive time intervals, saving these plots as images, and then combining them into a single animated GIF. This allows for a dynamic visualization of the brain activity over time.
And how do we know it's accurate?
The accuracy of the animation depends on several factors, including the quality of the EEG data, the correct application of the topomap plotting function, and the validity of the time window selected. Assuming the code is implemented correctly and the data is representative, the animation should provide an accurate visualization of the EEG activity over time. However, for precise interpretation, it's always important to consider the specific characteristics of the data and the methods used.
And how do we rerun the animation again?
To rerun the animation, you can simply execute the code cell again that contains the display animation command. This will reload the GIF animation and display it again for you.
How do we make sure it fits the screen better?
To make it fit the screen better, you could adjust the figure size when generating the topomap plots. By specifying a smaller figure size in the plotting function, you can ensure that the animation displays more appropriately within the notebook output area.
Welcome, curious minds, to the deep dive. Imagine, for a moment, being able to tune in to the subtle electrical whispers of your own brain.
Yeah, like listening in on its secret conversations.
Exactly. What if you could go on a scientific treasure hunt, not for gold, but for the incredible secrets hidden right there, inside those whispers? That's pretty much our adventure today. So our mission for this deep dive is to take this stack of technical notes we've gathered It feels almost like a forensic report from a data scientist, actually.
It kind of does, yeah.
And pull out the most fascinating nuggets of knowledge. We're going to walk you through the path, which, let me tell you, can be pretty tricky, from raw, complex brain data to actually understanding something meaningful.
And there were definitely some surprises.
Oh, yeah. Puzzles, roadblocks, the works. Think of it as a real behind-the-scenes look at how scientists turn those, squiggly lines into actual insights.
And our source material for today's exploration, it comes from this collaborative dive we did into publicly available EEG data, specifically from a fantastic resource called PhysioNet.
PhysioNet, right.
And we've been using some pretty powerful tools, Python libraries like MNE-Python and WFDB. This dive really shows how the pros try to extract knowledge from these incredibly complex data sets, warts and all.
Okay, let's unpack this then. Jump right into the brain's data trails. We're talking about electroencephalogram, or EEG, data. For anyone maybe new to this, what is EEG data, fundamentally?
Right. So at its core, EEG data is raw electrophysiological information. Imagine placing tiny sensors, these electrodes, on someone's scalp.
Okay.
These sensors pick up the incredibly faint electrical signals that the brain produces as neurons communicate with each other.
Wow, super faint.
Yeah, tiny voltages. And it's a continuous recording of that electrical activity. So it's like a direct, real-time window into what the brain is doing moment by moment.
A window into the brain. And where did we find this particular treasure trove of brain signals?
So our journey started on PhysioNet, which, as I mentioned, is just this amazing public resource for medical and scientific data. It's a huge open library, but specifically for biological signals.
Like heartbeats, brain waves, that sort of thing.
Exactly. And our specific quest began within a database there called EGOMB. We were looking for data from one particular person, subject S014.
Okay, subject S014, got it. So we're on the hunt. What were the first big finds when we started, digging into their directory?
Well, the initial success came pretty quickly, actually. We found and listed these records, specifically files ending in DIDF, that's the European data format.
Ah, EDF.
Yeah. Within the S014 directory, we saw, for instance, a file named S014R02.edf.
And that EDF file, that's the main thing, right? The core data file containing all those continuous EEG recordings.
That's exactly right. It holds all those squiggly lines representing brain activity over time. But here's where it gets really interesting, and where our little detective story began. Alongside these EDF files, we found these companion files. They had the same name, but with a .event extension added on, like S012 or 2.edf.event.
.event. Okay, the plot thickens. What are these mysterious .event files supposed to do? They sound important.
Oh, they are absolutely crucial, or they should be. These .event files are meant to hold what we call event markers.
Event markers.
Think of them like digital timestamps. They synchronize the continuous EEG data with specific things that happen during the recording.
Like what kind of things?
Well, for example, if the subject was asked to open or close their eyes, or maybe they saw a flashing light or pressed a button, an event marker would note the precise moment that happened in the EEG data.
Ah, okay.
Without these markers, you just have a whole lot of electrical activity, but no context. You wouldn't know what the brain was doing when.
Right, you just see the squiggles change, but not know why. That makes sense. So, okay, we found the core EEG data in the EDF file. The next logical step would be to actually load this brain data into our analysis tools, right? Did that first attempt go smoothly? Opening the evidence bag, so to speak.
Yeah. Thankfully, loading the main S014R02.edf file itself, that went fine. We used MNE-Python.
MNE-Python. Remind us what that is.
It's a specialized open source library, really popular in neuroscience. It's specifically designed for analyzing human neurophysiological data like EEG, MEG, that kind of stuff.
Gotcha.
So loading the EDF into MNE-Python was a success. And that was a major step, getting the raw data out of its storage format and into a structure we could actually work with.
Okay, great. And once it was loaded, what did we learn just from that initial look? Like, what kind of info does the raw data file itself tell us?
We learned quite a bit just from inspecting the header information. That's basically the metadata embedded within the file.
Like the file's ID card.
Exactly. MNE-Python makes it pretty easy to access. We could see critical details like the number of channels, that's how many electrodes were on the subject's scalp, in this case 64.
64 sensors, okay.
And the sampling frequency. That tells us how many data points per second were recorded for each channel. Important stuff for understanding the quality and scope of the data. It's like getting the basic map of our brain signals.
All right, so far so good. We've got the EEG data loaded. We know the basics. 64 channels, how fast it was recorded. But now, Now comes the part that really turned into a bit of a data science detective story.
Yeah.
The curious case of the unreadable event files. After loading the EDF, what was that critical next step, and what was the roadblock we hit?
Well, the critical next step was simple.
Yeah.
Read that S013R02.eds.event file. We needed those event markers to make sense of the EEG.
Right, for the context.
Exactly. But the roadblock was immediate. Just trying to read that .event file, bam, Unicode decode error.
A Unicode decode error. Okay, that sounds like the computer just threw its hands up. For someone like me, not deep in coding, what does that actually mean when you hit that with real data?
That's a really good question because it happens all the time in data science. It basically means the computer trying to interpret the file's raw bytes, the ones and zeros, as if it were human-readable text, like a standard document.
Okay.
But it couldn't understand the file's language, its encoding. It was expecting something common, maybe like UTF-8, but the file clearly wasn't written in that code.
So it's like trying to read a book written in an alphabet you don't recognize.
Exactly that. The computer knows it's supposed to be text, but the symbols don't make sense in the way it expects.
Okay, so how did you try to fix that? Was there an aha moment, maybe trying a different alphabet?
There was an aha for solving that specific error, yeah. But it immediately led to a deeper, much more frustrating mystery. We tried a common fix. We told the computer, okay, try reading it using Latin 1 encoding instead. It's another way of interpreting bytes.
And did that work?
Well, it solved the Unicode decode error. The program didn't crash anymore. It could technically read the bytes. But then the real puzzle was revealed.
Which was?
The file's content, even when read with Latin 1, was just not human-readable text. It was mostly gibberish, weird symbols.
What did it actually look like? Can you describe it?
It was mostly unprintable characters, but right in the middle of this binary mess, we saw this little snippet of actual text. XG hashtag time resolution, 160 II.
Whoa, time resolution, 160. That looks like a clue.
Exactly. That little string embedded in the chaos was the big realization. This wasn't a simple text log file we can just open and read line by line. It had some specific, unknown, non-standard binary format.
Binary meaning computer code, not text.
Good. To parse it correctly, to pull out those event timings, we needed to understand its exact structure, its layout, which meant we needed to find documentation for it. And that kicked off a real data science treasure hunt.
So you knew you needed the instruction manual for this weird file format. What did you try next to find clues? Where do you even look for something like that?
Well, we tried a few things available right there on PhysioNet.
All right.
We checked a file called sh256scms.txt.
What's that for?
It's mainly for verifying file integrity, making sure your download isn't corrupted. Useful, but unfortunately it offered zero clues about the .event files format.
Okay, dead end there.
Yep. Then we tried using another tool from the WFFDB library, a function called getRecordList, hoping it might programmatically list all the associated files, including the .event ones, maybe giving us a hint.
Yeah.
Mostly, it just listed the primary EDF files. Again, it sort of added to the mystery, really. How are these event files officially linked or accessed within the database structure if the tools don't easily see them? It felt like we were looking for a key, but the keyholes kept disappearing.
Frustrating. And you even hit another little snag, a classic data science quirk with the different function, WFDB.ard header, right? Tell us about that.
Oh, absolutely. And this wasn't even about the event files. This was just trying to read the header of the EDF file using a different library, WFDB. It turns out when using WFDB.ard header locally on an EDF file, it unexpectedly also required a separate .heo file.
A different header file, even though the info is inside the EDF.
Exactly. M&E Python didn't need it, but WFDB did, for the same task. It's a small thing, but it's a perfect example of how even standard tools can have their own specific requirements and quirks. You assume one tool works one way, another expects something slightly different. It just adds another layer to the detective work.
It really shows you have to know your tools inside and out. So, faced with this persistent .event file mystery for subject S014, what was the next logical step in your investigation? Did you, try another subject?
Exactly right. That was the next thought. Maybe S014 was just weird.
We decided to expand the search and look at another subject, subject S001, to see if this .event file issue was consistent across the database or just a one-off fluke.
Makes sense. And what did you find with subject S001? Same problem. Pretty much, yeah. We checked the directory listing for S001, and sure enough, we saw the same pattern. S001R01.edf paired with S001R01.edf.event and S0001002.edf.event. So these pairs seem standard for this data set.
Okay, so the structure is consistent.
Right. So we downloaded S00001R02.edf and its corresponding S001R02.eds.event file. Loading the EDF file, S001R02.edf, into M&E, no problem. Worked just like S0 4 times.
But the event file.
But the event file? Same story. We tried reading S001R02.edf.event, specifically reading it in binary mode this time, just to see the raw bytes directly.
And what did the raw bytes look like?
It was this sequence.
Yeah.
hashtag time resolution, 160. Right there in the middle of all that binary code stuff.
Yep, embedded right in the raw bytes. It's a unique clue, definitely, a potential search term if you were digging through documentation.
So it sounds like you had a fingerprint, but still no clear instructions on how to read the rest of the message. Precisely. It strongly suggests some kind of structured binary data with embedded metadata, but the problem was our automated process, the script we were running, couldn't just go off and search external websites like PhysioNet's documentation pages or Google for that string.
Ah, right. The code can't do the human part of the detective work.
Exactly. It highlights that even with all these powerful tools, sometimes that crucial step requires manual intervention, taking that unique string hashtag time resolution 160 and actually searching for documentation, forum posts, anything that mentions it. That's the human detective work still needed to crack the code.
It's like finding a single cryptic note in a treasure chest and realizing you need to go back to the library or maybe ask an old professor to figure out what language it's even written in.
That's a great analogy.
It's a fantastic reminder, isn't it?
Yeah.
Data science isn't just algorithms running. It's about persistent human curiosity. Okay, let's shift gears slightly. While that event file remains our unsolved puzzle for now, a key piece of the treasure was already in our grasp. The raw EEG data itself from the EDF file.
Right, the data we could read.
Exactly. So what did we discover once we successfully loaded that primary EDF file from subject S010, SRI1FRR02.edf, and actually got to see the brain's whispers in action?
Well, we shifted our focus to visualization. This is where it gets really cool, I think, where those electrical whispers truly become visible. We were able to plot the time series for multiple channels simultaneously.
So you actually see the squiggly lines.
You actually see the squiggly lines, rows and rows of them, each representing one electrode on the scalp, showing its voltage changing over time. It's quite captivating, honestly, like watching a complex rhythmic heartbeat, but, for the brain.
Yeah.
You can literally observe the brain's baseline activity, its natural rhythms, how they fluctuate.
That sounds amazing. And you mentioned you had an image, 64-channel Charbot.png, which shows where all 64 electrodes are placed on the scalp. How do you go from just seeing those lines to actually mapping the activity onto a head shape like that?
Yeah, that image is an electrode placement map. It's crucial because it tells us where each squiggly line is coming from on the scalp. Now, directly overlaying our Claude onto that specific PNG image, that's technically complex and not really a standard scientific visualization.
Okay, so not drag and drop.
No, not quite. But
Yeah.
M&E Python offers much more powerful built-in visualizations that are directly related to electrode placement. These are
Everything we do is available freely on BioniChaos.com. Please consider supporting me on Patreon, and don't forget to click like, subscribe, and comment.
Everything we do is available freely on BioniChaos.com. Please consider supporting me on Patreon, and don't forget to click like, subscribe, and comment.
These are what scientists actually use. They're called topographical maps, or sometimes just topo maps.
Topo maps. Okay, what exactly is a top map, and why is it so important for understanding brain activity spatially?
So a top map is essentially a visual heat map of brain activity, projected onto a stylized head shape. It shows how a specific measurement, maybe the average signal amplitude over a period or the amount of power in a certain frequency band like alpha waves, is distributed across the scalp.
Ah, like a weather map for brain activity.
That's a pretty good analogy. It takes the data from each of the 64 individual electrodes and cleverly interpolates or estimates the activity in the spaces between the electrodes. This gives you a smooth, color-coded map across the whole head.
So you can see patterns across regions?
Precisely. Imagine seeing a hot spot of activity consistently lighting up over the motor cortex area whenever the subject pressed a button. Or maybe a wave of rhythmic activity spreading across the back of the head, the occipital lobe, when they were looking at something. That's the power of a top map. It lets researchers literally see the spatial dynamics of neural activity associated with different tasks or states.
Wow. So while we couldn't just, stick our plot on top of that reference PNG image we had, M&E can essentially generate a much more scientific and precise version of that idea. It uses its built-in head model and the channel location info from our data file to create these informative heat maps.
Exactly. This is how scientists really see the brain's spatial activity, turning those abstract numbers and squiggles from 64 channels into meaningful visual patterns distributed across the scalp. It's incredibly powerful for interpretation.
It really sounds like it. What a journey this deep dive has been. Seriously, from hunting for brain data on PhysioNet, successfully loading it, grappling with that really intriguing, still unsolved mystery of the unreadable event files.
Still bugs me a little.
Right. And then finally getting to these powerful visualizations of the brain, signals themselves through top maps. It really highlights the challenges, but also the incredible rewards of real-world scientific data exploration.
It truly does, and I think this dive highlighted several key takeaways for anyone interested in this stuff. First, these publicly available data sets, like the ones on PhysioNet, they're just invaluable resources. For researchers, students, curious minds, they really democratize access to complex scientific data.
Absolutely. Couldn't agree more. And second, maybe the big one from today. Working with real-world data, especially scientific data, almost always involves some detective work.
Always.
You hit unexpected errors, frustrating roadblocks like that Unicode decode error, and you constantly need to understand very specific, sometimes poorly documented file formats, like those .event files. It's rarely just a straight path from A to B.
No, but that puzzle-solving aspect, figuring things out, that's honestly part of the fun, right? It makes the successes more rewarding.
True. Which leads to the third point. These powerful libraries like M&E Python, they are amazing. They enable incredible insights and visualizations. They help us take these complex raw signals and actually interpret them in meaningful ways. Even if getting the data into them has twists and turns, they're the tools that help turn the raw data into a story.
Well said. And finally, I think this whole experience, especially with the event files, teaches us that sometimes the most critical piece of information, the context, the when, the what was happening, can be hidden away in these unexpected, non-standard formats.
Locked away.
Yeah.
And unlocking it requires patience, persistence, and, that good dose of detective work. The best insights often come not just from running the standard code, but from asking the right questions, noticing the anomalies, and being willing to dig deeper when something doesn't make sense.
So what does this all mean for you listening in? We successfully loaded and actually saw the brain's electrical activity in fascinating detail using topo maps. But that key piece of the puzzle, precisely when specific things happened during the recording, remains locked away, for now, in those cryptic event files.
Which leaves us with a provocative thought, doesn't it? What other secrets might be hidden in data formats we haven't yet learned how to read? Not just in EEG, but in all sorts of scientific fields, and what breakthroughs might be waiting just beyond our current ability to decode them.
It makes you wonder. The quest for knowledge, especially in data science, it seems, is so often about solving one mystery, only to find another, maybe even more intriguing one, waiting right behind it to be uncovered.
Always more questions.
Always more questions, a perfect thought to leave you with. Thank you so much for joining us on this deep dive into the electrical whispers of the brain.
Thanks, everyone.
Until next time, keep that curiosity sparking.
Everything we do is available freely on BioniChaos.com. Please consider supporting me on Patreon, and don't forget to click like, subscribe, and comment.
Welcome, curious minds, to another deep dive. Today, we're not just sifting through data, we're taking a thrilling plunge into arguably the most complex and fascinating data source of all, the human brain.
That's right.
Our mission: to explore how we can take those raw, kind of squiggly brain signals and transform them into incredibly insightful and, honestly, surprisingly beautiful visual maps.
Exactly. We're embarking on a journey today to unpack the whole process of transforming raw electroencephalography, that's EEG data.
Right,
You know,
EGA.
those tiny electrical whispers from your brain. We'll walk you through the real-world challenges, the surprising detours, even some clever coding puzzles we had to solve,
Mm.
and ultimately create a dynamic animation that shows your brain's electrical activity quite literally dancing across the screen. It's really like seeing your thoughts in motion.
Wow. Imagine for a moment being able to literally see the electrical echoes of your thoughts sort of rippling and shifting across your scalp.
Yeah.
That's the ultimate payoff we're building towards today, and, well, trust me, it sounds like a wild ride.
It can be.
So let's kick things off right at the beginning. We've got this raw EEG data, but it's certainly not a ready-made masterpiece just waiting to be admired, is it?
Not at all. No.
Before you even dream of seeing those beautiful brain maps, what are the very first, foundational hurdles you hit when trying to transform that raw signal into something meaningful, like a top map, that colorful map of activity across the scalp?
Right, the top app.
It sounds like there's a lot of groundwork needed first.
You've hit on it perfectly. There's a definite and often challenging journey from those raw, kind of noisy signals to a coherent, interpretable image.
Okay.
For this deep dive, we faced 3 core technical hurdles right out of the gate, and honestly, they're common tripwires in this field.
Oh.
Think of them as the foundational building blocks you have to get absolutely right, otherwise your whole visualization just won't make sense, you know?
Makes sense. So what's the first one?
The first was ensuring that the specific electrode names in our dataset, like the ones labeled in RAW's 0402.chic names, perfectly aligned with a standard electrode map, like the standard 1005 montage.
Okay, so alignment. Why is that so critical?
Well, it isn't just about pretty names. It's like trying to assemble a puzzle where half your pieces are labeled for a different puzzle box entirely. If the system doesn't know exactly where each electrical signal is coming from on the scalp, your map will be skewed, or worse, just plain wrong.
Right. Garbage in, garbage out.
Precisely. We ended up having to implement a clever mapping technique, often using something like a Python dictionary, to meticulously clean up and rename our channels. We used a method called strip just to clean up some trailing periods.
Oh, little details like that.
Exactly. To achieve this crucial alignment, it's the data cleaning step that truly makes or breaks your analysis later on.
Okay, so channel names, get them right. What was hurdle number 2?
Second was accurately calculating the power spectral density, or PSD, for the brainwave bands we were interested in.
PSD, okay, power spectral density. Break that down a bit.
Sure, it sounds a bit technical, but think of it like tuning a radio to isolate a specific frequency.
Okay.
Imagine you want to isolate just the alpha waves, which are usually found between, say, 8 and 12 hertz.
Right. Alpha waves often linked to relaxation.
Exactly, that relaxed but awake state, like when you're just chilling out with your eyes closed. This involved precisely defining our time windows and frequency ranges. We used the Welch method, which is pretty standard for this calculation. Getting this right is absolutely vital for isolating the specific brain activity we actually want to visualize without all the, the noise from other brain rhythms interfering.
So you're filtering out the noise to see the signal you care about. Makes sense. And the third hurdle.
And the third hurdle was getting the top map plotting function itself to correctly map that isolated brain activity onto a scalp diagram.
Ah, the actual plotting.
Yeah. This required precise channel location information, which, again, comes from that standard 1005 montage we just talked about. If the names are right, the locations should be right.
Right, it all connects.
And a neat trick we actually used here was creating a mock evoked array object.
A mock object, what's that?
Well, in the MNE Python library, which is a popular tool for this,
Okay.
evoked objects typically represent the brain's average response to a specific event or stimulus, like a flash of light.
Okay.
By simulating the structure for our continuous data, we could cleverly leverage MNE's powerful built-in plotting functions, even though our data wasn't strictly an evoked object in the traditional sense.
Ah, so you tricked the tool into working for you. Clever.
Kind of. It's like giving a specialized tool a slightly different but compatible input so it can still do its amazing work.
Okay, let me try and summarize. It really sounds like trying to teach 2 different dialects of the same language to understand each other, or making sure all your puzzle pieces are genuinely from the same box, as you said.
That's a great analogy. Yeah.
Because if the coordinates are off or the names don't match, your map is just meaningless colors.
Pretty much.
When you first started digging into this specific data set, did you run into any immediate roadblocks? Like, what was the first sign you actually had a problem?
Oh, absolutely. The very first hint that our puzzle pieces weren't quite fitting came as a value error. Python loves throwing those.
Doesn't it just?
And it loudly proclaimed, the following electrodes have overlapping positions.
Okay.
That message was our clear signal that, despite our careful planning, we still had some deep-seated mismatch issues to sort out with the channel locations, probably stemming from those initial naming discrepancies we talked about.
Right.
It was the moment we knew we needed to put on our serious detective hats.
That error message sounds like the universe telling you, hold up, go back to the drawing board. How did you pinpoint the exact mismatch? Was it like pulling a thread or more like, I don't know, forensic analysis?
It definitely felt more like forensic analysis. This is where the detective work got truly fascinating and, gotta admit, a little frustrating too.
Yeah.
We literally had to compare the channel names from our specific data file, the WFDBKL file for this deep dive, against that comprehensive standard 1005 montage.
Okay.
Now, our data set had 64 channels. The standard montage lists a whopping 343 channels.
Wow, 343, that's a big difference.
Huge. It's like trying to find specific addresses in a small village using a map of an entire continent.
Okay, yeah, good luck with that.
Exactly. And what we found was a genuinely surprising fact. Only 36 channels are common to both lists.
Wait, only 36 out of 64.
Only 36. Think about that. Less than half of our dataset's channels actually mapped directly to the standard.
No.
We quickly identified the misfits 28 channels in our dataset that simply weren't in the standard montage. They often had very specific prefixes like A, CP, FC, FTPO, and TP.
Ah, so different naming conventions entirely.
Seemed like it. It was a real aha moment, but
Yeah.
also a kind of uh-oh moment because the top map did eventually plot, which was a good sign.
Okay.
But it was based on the severely limited subset of just 36 channels.
Right. So what does this all mean for you, our listener? Whether you're trying to interpret these brain maps yourself or just understand the journey of dealing with complex data.
Yeah, this is crucial.
It's like trying to, I don't know, diagnose a complex electrical fault in a house by only checking like 10% of the wires.
That's a good way to put it.
You might get some information, but you're missing a huge portion of the picture.
Absolutely.
This experience really highlights why precision matters so much in data alignment. Even a tiny discrepancy can dramatically change what you're able to see, interpret, and ultimately understand from your data.
Mm-hmm.
It really underscores that simply getting a plot to appear isn't enough. It has to be a meaningful and ideally a complete plot.
Couldn't agree more.
So we've debugged the static image. We've got our 36 channels mapped. That's a huge win. We can now get a snapshot of brain activity.
Right, a snapshot.
But the brain, as we know, is anything but static, isn't it?
Definitely not.
It's a dynamic, ever-changing landscape of electrical activity. So how do we take this snapshot and turn it into a moving picture?
Mm-hmm.
What's the next big technical leap you had to tackle?
Yeah, that's the goal, right?
To move from a single moment to understanding how brain activity changes over time, especially related to specific tasks, like, say, imagining moving a hand. This leads us to event extraction and epicing, I assume.
Exactly. Event extraction and epicing. This step is absolutely vital for analyzing brain responses to specific events.
Okay.
Whether it's a simple flash of light, a sound, or in this particular case we looked at, a motor imagery task, thinking about moving your hand.
Right.
Our first attempt to extract events, these are specific timestamps in the data that mark when something significant happened.
Mhm.
From the data's annotations, it yielded only one event, surprisingly labeled T0, just one.
T0. That sounds incomplete.
Right. And frustratingly, its corresponding epoch, that critical short segment of data around that event that we wanted to analyze, was immediately dropped. We got a no data error.
Oh no, after all that channel work.
Exactly. It was a real head scratcher. Like, what does T0 even mean here, and why is there no data around it?
So what did you do? Dig deeper.
We had to. That dropped epoch led us on a deeper dive into the raw.event files themselves. These were separate files alongside the main EEG data.
Okay.
We discovered they contained custom binary data, not just plain text.
Binary, ugh, never fun.
Tell me about it. And it also mentioned a time resolution that felt a bit unusual, 160 units per second or something like that. We tried interpreting the binary content, attempting to read segments as integers to maybe find event timings or codes. We even managed to interpret the last 8 bytes,
Okay.
which seemed to correspond to an event ID of 1, which actually matched the T0 we saw in the other annotations.
Ah, so T0 means ID1 progress.
Sort of. But here's the kicker. The time value we extracted for this T0 seems really unusual. It didn't look like it was representing a typical, epochal event onset time.
Like the start of the hand movement thought.
Exactly. And that no data error we kept getting. It further screamed that this T0 in the .event file wasn't what we needed to segment our data effectively. It wasn't the marker for the task itself.
So you hit another wall. This is where it gets really interesting, though, right? Because it's a fantastic universal lesson for anyone working with data, not just brain signals.
Absolutely.
It's not just about crunching numbers or fixing code. It's about understanding the entire scientific experiment, the context, the why.
Precisely.
It's like being a detective solving a mystery by finally finding the missing manual. Without that fundamental understanding of what the T0 or maybe a T1 or T2 code actually means in the context of the experiment,
Right.
all the technical skill in the world wouldn't let you interpret what was happening. It truly brings the science into data science.
Exactly. This pointed to a crucial insight. We couldn't just guess or infer the meaning of these codes. We needed to consult the official documentation.
The dreaded documentation.
Sometimes it's your best friend. In this case, for the EEG motor imagery dataset on the PhysioNet website. That's where you'd find the definitive details on the experimental protocol, the precise timing of stimuli, and the true meaning of those event codes. For instance, finding out that T1 likely meant left-hand imagery and T2 meant right-hand imagery.
Okay, and now, W, you can actually analyze the task.
Exactly. That moment when you realize the answer isn't hidden in your code, but in, like, a dusty PDF on a website. It's humbling, but also incredibly satisfying.
I can imagine it's the core of what makes data science science.
Totally.
Okay, so after all that intricate detective work, the painstaking alignment, the deep dive into event timing, finally it's time for the payoff.
Yes, the fun part.
We've tackled the static images, we've grappled with the elusive event data. Now, how do we bring it all to life by visualizing the temporal evolution of EEG data through animation?
Yeah.
This is where we actually get to see the brain doing its thing. This sounds amazing.
This was the exciting goal, the grand finale of our data journey, to create a truly dynamic view, seeing the brain's electricity flow across the scalp like a digital dance.
The digital dance of the mind, I love it.
Our plan was simple in concept, but, required precision in execution.
Always the way.
Select a raw data segment, say, the first 5 seconds from our S01R02 file. Then, the trick was to generate a whole series of topomap plots for small, successive time intervals within that window.
Okay, like frames in a movie.
Exactly. Think of it like creating a flipbook, where each page is a tiny snapshot of brain activity at a slightly different millisecond.
Cool.
Finally, the magic happens by combining all those individual plots into an animated GIF using a standard image processing library like Imagio.
Okay, so loop through time, make a plot for each tiny step, stitch them together. Sounds straightforward enough, but I bet there were some last-minute coding hurdles, weren't there?
Oh, you know it.
The nitty-gritty that makes it all work, that often surprises you right before the finish line, because that's the reality of working with complex data.
Yeah.
It's rarely a straight line.
Oh, absolutely. You
So-
think you're there, you've climbed the mountain, and then the code throws a couple more curveballs just for fun.
Yep.
I vividly remember hitting a particularly frustrating type error related to unpacking the plot figure. It was like the plotting function was just shrugging its shoulders saying, I don't know what to do with this input.
Classic.
And then came a value error about invalid time ranges in the plotting loop itself, basically telling us, hey, you can't ask for a brain map that's 0 seconds long, which, fair enough.
Right, you got to give it some time to plot.
Exactly. It's those little moments of despair followed by the aha when you realize the subtle misstep that truly define working with complex data.
Definitely.
But after some meticulous adjustments to how the plots were generated and how those tiny time windows were defined, we celebrated a triumph. 50 top map frames successfully generated.
Nice. 50 frames.
Each frame, a tiny, perfect piece of the brain's dynamic story over those first 5 seconds.
And the result is
Yeah.
this dynamic animation that shows how brain activity actually changes over time, which is so incredibly powerful for understanding what the brain is doing during tasks like motor imagery.
It really is.
Imagine how cool and genuinely fun it is to watch those electrical signals ripple and shift across the scalp in what feels like real time. It's like that digital dance of the mind you mentioned. We can even save this captivating animation as a GIF, right? And maybe adjust its display size if needed to make sure it looks absolutely perfect on screen.
Yep, save it as a GIF, share it, analyze it. That's truly seeing your brain in action.
What an incredible journey we've taken today, seriously. From wrestling with mismatched channel names and deciphering mysterious binary event files,
Yeah.
all the way to creating a living, breathing animation of brain activity. It truly highlights the fascinating blend of technical skill, relentless problem solving, and sheer scientific curiosity required in this field.
It really does.
It's a powerful reminder that data is never just numbers. It's a story waiting to be told if you're willing to do the detective work.
Well said. And this deep dive into EEG data visualization really highlights that the human brain isn't just a static collection of regions like you see in some textbook diagrams.
Right.
It's a constantly shifting, dynamic landscape of electrical activity. What's fascinating here, I think, is thinking about how seeing this dynamism, this digital dance, could open entirely new doors.
Like what kind of doors?
Well, whether it's understanding neurological conditions like epilepsy better by observing how seizures actually propagate across the brain,
Right.
or designing more intuitive brain-computer interfaces that could help people control devices just with their thoughts.
The BCI stuff is amazing.
Or maybe just deepening our appreciation for the incredible complexity happening inside our heads right now, every single second. It's quite something.
It really is. And for you, our listener, think about how these visualizations aren't just cool to look at, right? They could potentially help us not just understand the brain in general, but maybe even personalize interventions or training based on an individual's unique brain activity patterns.
That's a really exciting frontier.
Imagine optimizing learning or even rehabilitation after injury by actually seeing how a specific brain responds to different approaches.
The possibilities are huge.
Definitely something for you to mull over until our next deep dive. Keep those neural networks firing.
Okay, so we do have a human in the loop, just if you were wondering. We had some questions, but they're fairly generic, so I might get the robot. Hopefully the robot already answered those. Like, what is this? Is this channel operated by AI? Will it be possible for you to share the call-up link post live session? I don't know, I haven't tried it before. Maybe. And yes, we are developing this website. That's the main reason we are here. And eventually, if anything interesting comes up of this, which is already is, so it's probably going to eventually go on to BioniChaos.com. So, yeah. So if you have any more specific questions, especially after visiting the site, I'll be more than happy answering those.
Everything we do is available freely on BioniChaos.com. Please consider supporting me on Patreon, and don't forget to click like, subscribe, and comment.
And you just have to do whatever the AI lady said. Otherwise, we get, oh yeah, there's a subscriber. So it does work. I've had 2 likes as well, so not sure what prompted that, but yeah. So we doing reviews. Obviously this is Notebook LM. Go check it out. I don't think it needs advertising. Well, Google ads are probably everywhere now, because they're really pushing hard. We do have another review of what we were doing here in this project, like a summary bit. We're obviously not reading any text. Well, why would you? If you have such great models. This data set we didn't have much luck with because we couldn't actually pass the edf.events files. Apparently it's a common issue. I don't know if it's only an issue with all the data, but yeah, there's something wrong with it. And yeah, if anyone knows how to solve it, do let me know. Then we can do more with this particular data sets. Otherwise, we'll be looking at other data sets, primarily open access on the PhysioNet. Yeah, open data sets. We might actually review, get the bot to review this and actually potentially choose one that might be useful for us. So yeah, let me know if there's any questions. I normally lose viewers when I start talking, but somehow the professional podcasters, they get traffic going, so why not?
Hey everyone, welcome back to the deep dive. If you've ever felt like you're just swimming in data, trying to figure out what's genuinely valuable, or maybe just really fascinating, then you know the feeling. How do you actually find those hidden gems, those insights that make you pause and think, wow, okay, I never saw it that way before? Well, today we're doing just that. We're diving deep into an incredible collection of sources, open medical and physiological signal databases. And we're not just looking for data that's, useful. We're hunting for the stuff that's genuinely interesting, the kind that reveals something surprising about us, about our bodies, about how we interact with the world. So our mission today, uncover those surprising facts, those maybe unexpected applications hidden in these databases, help you see the huge potential they hold. We've got this amazing catalog to work from. It really is like a treasure map for data nerds, covering everything from ECGs to brain activity, posture, you name it. So looking through this list, what immediately strikes me is just the incredible variety. I mean, when most people think medical data, they probably picture heart monitors, blood pressure cuffs, that kind of thing, right?
Right. The standard stuff.
But this collection just blows that wide open, shows you how much more our bodies are constantly telling us.
You've really hit on something key there. What's so fascinating, I think, is how these databases capture the really subtle signals, the powerful little whispers from the human body and how it interacts with everything around it. It makes you ask, what unique perspectives do some of these offer? Things you just wouldn't get from a standard medical chart.
Okay, let's jump right into some of those unique measurements then, the ones that go way beyond the heartbeat. We've got one here called a pressure map dataset for in-bed posture classification. So this isn't about your usual vital signs. It's capturing continuous pressure sensor data. 13 people, different sleeping positions.
Interesting. So pressure maps.
Yeah.
What's the surprising thing there?
Well, what the data seems to reveal is pretty specific. These tiny pressure shifts during the night, they seem surprisingly crucial for really restorative sleep. It suggests that even like minor tweaks in mattress design or how someone's positioned could make a huge difference for sleep quality, especially if they have mobility issues.
Wow. That's a level of detail you just wouldn't get from, say, a fitness tracker counting sheep. That's a perfect example of that granular insight. And building on that, think about this one. Continuous cuffless monitoring of arterial blood pressure via graphene bioimpedance tattoos.
Graphene tattoos. Okay, no, that sounds futuristic.
It really does. But it's actual research. They're using these tiny graphene sensors on the wrist. It gives raw-time data for 4-channel bioimpedance signals, basically measuring electrical signals in the tissue, along with continuous blood pressure and PPG. That's the light-based heart rate thing, from 7 subjects.
At least 7 subjects.
Yeah, it's a small group, but what's compelling is even with just 7, the continuous readings are hinting at individual blood pressure patterns, like during sleep or activity, patterns that you'd totally miss with just occasional checks in a clinic.
Right, the usual snapshot versus the whole movie.
Exactly. It's moving towards this truly personalized view of cardio health. A continuous story, not just isolated moments. That feels like a big shift.
Okay, this next one really gets me thinking. How much does our environment, like the music we listen to, subtly mess with our heads or help them? It's a multimodal data set for investigating working memory and presence of music.
Oh yeah, I saw that one. Multimodal, so lots of different signals.
Yeah, it combines FNIRS data that's functional near-infrared spectroscopy, using light to see brain activity with stuff like skin conductance, heart rate, PPG,
Okay.
all collected while people did these end-back memory tests. But here's the twist. With music playing.
Okay, so not just resting state.
Right. And this data set lets you actually analyze how something as common as background music might be, subtly helping or hindering our focus, our processing power. It's a pretty cool insight into our daily cognitive performance.
You're right, that's fantastic for looking at environmental effects. And there's another one that touches on this interaction too. The body sway when standing and listening to music modified to reinforce virtual reality environment motion. Bit of a mouthful.
Yeah, just a bit. What's the core idea?
Well, the data showed that when music was tweaked, subtly changed, to match the motion someone was seeing in a VR headset,
Okay.
it actually increased how much their body swayed, even though they were standing perfectly still.
No way. So the music tricked their body.
Kind of. It shows just how deeply linked our physical responses are to what we perceive, even if it's virtual. Taken together, these data sets let you explore that subtle dance between our senses, our bodies, and technology. It's kind of surprising how easily our physical state can be nudged by perception.
It really is incredible how specific some of these get. Let's shift gears a bit. Some databases seem designed to really understand specific human behaviors or conditions. Give us that objective window into, well, what makes us tick, like this one, the Stress Recognition in Automobile Drivers Database.
Yes. Driving stress. Relatable.
Totally. They collected all sorts of recordings from healthy people just driving a set route. We've all felt that stress. Someone cuts you off. This data set isn't just theory. It's trying to quantify that real, everyday stress in a dynamic setting, which gives unique insights into how our bodies actually react under real-world pressure, not just in a lab.
And it's not just external things like traffic, right?
Yeah.
They also let us pinpoint reactions to very specific internal states, like the electrocardiogram, skin conductance, and respiration from spider-fearful individuals watching spider video clips.
Oh, wow, that's specific.
Very specific. And the data was used to build an algorithm to detect anxiety levels in real time, just from biosignals.
So reading fear from the body's signals.
Essentially, yes.
Yeah.
And the compelling insight here is how these objective signals can potentially quantify something as subjective as a phobia or maybe even generalized anxiety. It sort of points towards personalized, real-time mental health tools that go beyond just asking someone, how anxious are you?
That is powerful. And speaking of complex states, this one sounds intense. The behavioral and autonomic dynamics during propofol-induced unconsciousness dataset.
Yeah, that one's fascinating.
It tracks multiple signals, heart rate variability, skin conductance, using some advanced stats, point process indices.
Right, complex analysis.
From 9 people getting propofol sedation, controlled unconsciousness.
And the striking thing there.
How the data can actually map that journey
Well,
into unconsciousness and back out again. It's like peeking behind the curtain of awareness with objective, measurable data.
exactly. It gives objective insights into these really complex states that, used to be mostly about just clinical observation.
A big leap.
It really highlights that shift, moving beyond subjective description to actual measurable, analyzable data for understanding and maybe intervening. And this includes super specific things too, like the effect of deep brain stimulation on Parkinsonian tremor.
Right, measuring tremor velocity in Parkinson's patients getting DBS.
Yeah, and the data there quantifies just how much those targeted electrical pulses can directly reduce those debilitating tremors. It's direct evidence of the treatment working, signal by signal.
It's clear that precision can lead to surprising insights, but then sometimes it's just the sheer scale that's mind-blowing and opens up different doors. We also see these massive clinical databases. They offer a whole different kind of insight, don't they?
Absolutely. Scale matters.
The MIEP family keeps popping up everywhere in our sources. MIEP3, MIEP4, the ECG one, the ED one.
They're giants in the field.
Huge collections. Physiological signals, clinical data from tens of thousands of ICU patients. The volume alone is just staggering.
And what's so valuable about MIM, it isn't just the size, though that's huge. is how comprehensive they are. Take the MIM4 ECG module. It has something like 800,000 ECGs from nearly 160,000 unique patients. That scale. It lets researchers dig into critical care physiology, look at outcomes in a way that's just impossible with smaller sets. The big question this kind of data helps answer is, how do we use all this interconnected information? How do we find those subtle diagnostic clues or optimize treatments in ways that really change patient care?
That's where machine learning really comes into play, I guess.
Definitely. It's fertile ground for AI in healthcare.
And it's not just critical care either. There's the PTB-XL dataset, large public ECG database.
Right, another big one.
Over 21,000 ECGs, nearly 19,000 patients. And crucially, annotated by cardiologists with 71 different classifications.
Which is vital for training algorithms.
Exactly. An incredible resource for studying arrhythmias, maybe spotting rare conditions. And then there's the Essentia 11K single-lead continuous raw electrocardiogram dataset. 11,000 patients, 2 billion labeled heartbeats.
2 billion.
The surprising power of these massive data sets, I think, is finding those super rare patterns or subtle things the human eye might just miss, even an expert's eye, which is why they're accelerating this hyper-accurate diagnostic AI development.
Precisely. These large-scale data sets are absolutely critical. You need them to develop and, just as importantly, validate advanced algorithms. They let us spot patterns, anomalies that are almost invisible in smaller studies. Take the CHEX mask database, for instance. Over 650,000 chest x-rays uniformly annotated with segmentation masks.
Segmentation masks, so outlining specific areas.
Exactly. Done using an advanced AI model, HybridGene, with quality control built in, those masks are vital for training AI in medical imaging. Makes the AI smarter, more accurate, more efficient at diagnosis.
So it's like human expertise combined with AI, but at a massive scale.
Right. Creating resources for medical imaging innovation that, frankly, just didn't exist before. It's pretty remarkable.
Okay, shifting focus again slightly. Beyond pure medical conditions, some data sets are tackling really fascinating areas, like human-computer interaction, or even big social issues.
Yeah, the applications get broader.
The EEG motor movement imagery dataset from 109 volunteers, or this big P3BCI dataset, brain-computer interfaces.
DCI, yeah. Paving the way for direct brain control.
That P300 signal they mentioned in the BCI one, that's the brainwave spike when something unexpected happens, right?
It's the one. A kind of aha signal from the brain.
And these datasets are showing, quite uniquely, I think, just how precisely those brain signals can potentially be translated into commands. For assistive tech, for neuroscience, it pushes boundaries.
Indeed, BCI datasets are right at the cutting edge. Assistive tech, understanding the brain, showing those direct links between thought and action mediated by tech. But here's one that feels particularly thought-provoking, maybe even vital, for its societal impact. Q-pain.
Q-pain, a question-answering dataset to measure social bias and pain management. Okay, that title says a lot.
It really does. It directly confronts this critical question. Do unconscious biases, maybe around race or gender, actually influence how pain is treated?
How does the dataset do that?
Well, it's designed so researchers can swap in different patient profiles, different races, different genders for the same clinical scenario, and then see if the decisions about prescribing pain medication change based on those profiles alone.
Wow. So it's designed to reveal bias, if it exists.
Exactly. It offers a measurable way to see if systemic inequities are baked into clinical decisions. It's a powerful use of data to potentially uncover and address unfairness in healthcare. Finding a path towards more equitable care, that feels incredibly important and maybe one of the most interesting applications we've seen.
So what's the takeaway from all this? It's clearly not about finding the single best data set, is it?
No, I don't think so.
It's more about appreciating the unique angle each one offers, the challenges, the opportunities, from understanding how music affects our balance to mapping unconsciousness to detecting potential bias in prescribing painkillers. These databases are like windows into incredibly complex systems. They give us these glimpses, these insights we just didn't have before, showing that interesting isn't just about size. It can be in 7 subjects with graphene tattoos or 2 billion heartbeats. We've really journeyed through an amazing collection today. Open medical, physiological signal databases. We've seen data showing nuances of sleep, hidden signals of anxiety, the complexity of brain function, even that potential for bias in medical decisions. Each one, big or small, clinical or experimental, it offers a unique lens, a different way to view the human experience, often with surprising and deeply impactful insights.
And, knowledge is really most valuable when it's understood and applied. these open data sets. They democratize access. They give everyone the raw materials for scientific discovery. It creates this fertile ground for innovation across so many fields. Accelerates research by making complex info available to, well, anyone with the skills and curiosity to use it. Turns potential into actual progress.
Thinking back on all these, what really stands out to you? It feels like the surprising facts are just scratching the surface sometimes.
Definitely. They hint at deeper connections, maybe applications we haven't even thought of yet. We're just beginning to unlock what's hidden in there.
So that leaves us with a question for you listening. If you had access to any of these incredible data sets, what big question would you try to answer? What new insights could you maybe uncover? Something that might change how we understand health or behavior? Or maybe even humanity itself? The future of discovery, it seems, really is in the hands of those willing to dive deep.
There is a human in the loop, just in case you have any questions or want to let me know which dataset you like. And you go check out the website that we are making.
Everything we do is available freely on BioniChaos.com. Please consider supporting me on Patreon, and don't forget to gently click like, subscribe, and comment.
Gently, it's the important one. This is obviously VO3. So I have to listen to what the robot is saying. We have a quick overview of what the website is all about, so we might go on to that one, because every time I start talking, we start losing viewers, which is interesting.
Okay, think about this. How do you take really, really complex technical information, the kind that feels like you need a PhD just to read the first page? And how do you make that not just understandable, but actually engaging, maybe even fun? That's exactly what we're exploring in this deep dive. We're looking at a platform, BioniChaos. It seems to be doing something pretty cool with how we handle dense biomedical data, tech, and even education. It's not just about learning facts, it's more about finding new ways to, play with knowledge, making it genuinely enjoyable.
Exactly. And what's really striking here, I think, is the move away from just, well, static things like PDFs or textbooks. Instead, imagine dynamic simulations, visual tools where you can actually see what's happening, where you can manipulate complex biomedical ideas, explore them. It makes abstract concepts feel almost
Real.
tangible, like a digital sandbox, really.
Right, a sandbox. I like that. Okay, let's dig into an example. Fourier series. Anyone who's wrestled with that math. Trying to picture how complex signals break down into simple wave, it's notoriously tough. But BioniChaos has this high-fidelity Fourier simulation. You literally watch signals in the time domain decompose into frequencies. You see those epicycles, those basic circles building up complex shapes happening right there. It's such an immediate aha moment for understanding signal composition. Super important for diagnostics, too.
It absolutely is. It's a completely different way to get your head around signal decomposition. A huge shift. And then building on that, think about their interactive guide to EEG tech, trying to grasp the differences between, say, delta, theta, alpha, beta brainwaves just from a book. It could be so abstract. But with this tool, you can manipulate the parameters and actually see how these different brainwave patterns show up. It makes their clinical meaning much more obvious, much faster. You're visualizing electrode placement, exploring brain states directly. It's very hands-on.
That hands-on part feels key, doesn't it? And it's not just for brainwaves, right? This idea of visualizing signals works elsewhere too. They've got an ECG simulator, so you can mess around with different heart rhythms, tweak electrophysiological settings, and you instantly see how that changes the ECG waveform. It gives you this unique insight into how heart conditions actually affect the electrical signals. It really is like having a virtual heart lab on your screen. You can understand the mechanics without any risk involved. Pretty amazing.
It's definitely a powerful way to learn, to really master complex physiological systems, because you're interacting with them, not just reading about them and, even just dealing with massive amounts of information. That can be overwhelming. But their multimodal medical data landscape tool, it lets you explore diverse data sets interactively. You can see where the data gaps are, figure out ways to connect different types of information. That's so crucial for developing new health tech. It sort of turns data analysis from a chore into more of an engaging exploration, finding the fun of discovery again.
So pulling this all together then, what we've seen in this deep dive is just how powerful these kinds of interactive tools can be. They take really intricate subjects, signal processing, brainwaves, heart rhythms, navigating huge data sets, and make them feel intuitive, almost like a game. It feels like a shortcut to truly understanding things, sparking those aha moments that actually make learning stick, make it exciting.
Indeed. It really underscores that knowledge isn't just something you absorb passively. The real value comes when you actively explore it, play with it, understand it deeply. So here's something to think about, a final thought maybe. How could this approach to learning, the one emphasizing visualization, simulation, real-time interaction, how could that change how we understand any complex field, not just biomedicine? Imagine tackling complex engineering or physics or even art history by interacting with it, by essentially playing with the core concepts, making deep knowledge accessible, and maybe even thrilling for everyone.
Everything we do is available freely on BioniChaos.com. Please consider supporting me on Patreon, and don't forget to click like, subscribe, and comment. Everything we do is available freely on BioniChaos.com. Please consider supporting me on Patreon, and don't forget to gently click like, subscribe, and comment.
Imagine, if you will, looking deep inside the human brain. Not with a surgeon's touch, though, but with pure data.
Yeah, what if you could actually see the electrical whispers of thought? Or, the intention behind imagining a movement?
It really does sound like something out of science fiction, doesn't it?
It might seem that way, but it's surprisingly within reach. It's just a really intricate process, starting with, very sensitive measurements.
It really is. And that's exactly what we're going to dive into today. Welcome, everyone, to our deep dive into the fascinating world of EEG electroencephalography. Our mission for you today is basically to unpack a whole stack of technical sources that detail this journey, acquiring, processing, and then visualizing real EEG data.
Yeah, and it's not just about listing the steps, right? It's about seeing how you actually transform those raw, sometimes messy brain signals into something meaningful, something you can even visualize in a pretty stunning way.
Okay, so the big question we're tackling is, how do you take these tiny electrical impulses, often buried in noise, and turn them into something you can actually see and, well, understand?
Exactly. It's a bit like being a data detective, honestly. You're deciphering this kind of secret language. You find surprising things, you hit roadblocks, but then you get these incredibly satisfying moments of discovery.
I love that data detective. It really feels like that sometimes. You're solving puzzles, maybe hitting unexpected walls, but then having those amazing aha moments when it all clicks. So let's start this journey.
Let's do it.
Okay, so our adventure, our quest into the brain's electrical world, it begins like many quests do, hunting for treasure. But this isn't gold, it's digital. We needed raw brain data.
Right. And our search led us to this fantastic public resource, the PhysiNet EEG motor movement imagery dataset. It's like finding a huge digital library just full of brain activity recording.
A library, okay.
Yeah.
And within that library?
We zoomed in on one specific file, S001R01.edf. This file is just one recording from one person doing a specific task involving moving and imagining movement. A really good place to start.
Gotcha. So how did you actually get your hands on it?
Well, we used a pretty standard tool in the Python world, Regedit, for the download. But here's where you get that first little real-world twist.
Ooh, what happened?
The file downloaded as a .zip archive, or at least that's what the system thought it was.
Ah, okay, so what was it actually zipped?
Exactly. It's a common thing, assuming file types. We had to look closer, inspect it, and realize, oh, this is actually an EDF file, European data format.
EDF. And that's important because
It's a standard format for medical time series data. Knowing it's EDF tells you a lot about its structure right away. It's designed for this kind of work, which is, well, crucial for sharing and comparing results in research.
makes sense. So you've got the right file, correctly named. What's next? Loading it up.
Yep, time for the first look. We used MNE Python for this. It's a really powerful open source library specifically built for analyzing EEG and also MEG data magnetoencephalography.
Right, MEG measures the magnetic fields, often used alongside EEG. So what did MNE Python tell you initially about this file?
Some really cool stats right off the bat. 64 channels.
64, wow. That's like having 64 tiny microphones listening all over the scalp, right?
Pretty much. 64 highly sensitive antenna, picking up those faint brain signals. It gives you incredible spatial detail.
Okay, 64 channels. What else?
They were recording at a sampling frequency of 160 hertz.
So 160 times every second for each of those 64 channels?
Exactly. Capturing the brain's electrical activity really fast. And the whole recording was about 61 seconds long.
Okay, so those numbers, 64 channels, 160 hertz, 61 seconds, they tell you about the richness of the data, the detail.
Absolutely. High temporal resolution from the sampling rate, good spatial resolution for the channels. It's a really high-fidelity snapshot of what the brain was doing over that minute. You can capture quick changes and get a better idea of where things are happening.
Okay, so we have this rich, raw data, 64 channels, brain whispers, 61 seconds. But you mentioned raw data is rarely clean, right? It's noisy.
Oh, definitely. Like trying to tune into a faint radio station with lots of static. That's why the next step, pre-processing, is so critical.
Yeah.
Cleaning up the noise.
Right, gotta get rid of the static. How do you do that?
Well, one of the first big steps is applying a filter. We use what's called a bandpass filter, specifically letting frequencies between 1 and 40 hertz pass through.
Okay, 1 to 40 hertz. Why that specific range? Is that where the interesting brain stuff happens for, like, motor tasks?
Exactly. That range covers many of the well-known brain rhythms involved in thinking and moving things like alpha waves, beta waves, theta waves. By focusing there, we cut out really slow drifts, maybe from sweat or electrode movement, and also the really fast high-frequency noise, like muscle twitches or electrical interference from lights and computers. It boosts the signal we care about.
Okay, so it's like tuning the radio dial precisely to the station you want. Makes sense. What else is involved in this cleanup?
Well, we also took a really close look at the EDF header information. The file's metadata.
Like reading the label on the specimen jar.
Exactly like that. It tells you vital details, how the data was collected, how the electrodes were referenced, specifics about each channel. You need that context for correct interpretation.
Got it. And did you look beyond just this one EDF file?
We did. To really get the full picture, we needed more context from the broader PhysiNet database. So we brought in another Python tool, the WFDB library.
WFDB. What did that let you do?
It let us explore the whole database programmatically. We could list all the different recordings, see what else was there. And importantly, we downloaded some related files.
Like what?
Like an image file 64-channel harbor.png. It actually shows you exactly where those 64 electrodes were placed on the person's scalp.
Ah, the map. So you know if a signal's coming from the front or the back of the head.
Precisely. It uses a standard system, the 1005 montage, which means the placement is consistent, allowing us to compare our findings and understand the spatial origin of the activity. It's the blueprint, like you said.
Okay, the map. What else?
We also got a records file, basically just an index, and crucially, a WFDB TAL file.
WFDBT cal.
Calibration.
Exactly. Channel calibration information. It ensures the raw voltage readings from each sensor are accurately converted into standard units, like microvolts. Accounts for tiny differences between sensors. It's all about getting accurate, reliable data.
Right. Building that full, accurate picture.
Yeah.
Okay, so now things get interesting. You mentioned a puzzle.
Ah, yes. The puzzle. This involved a different file. S001R02.edf.event. the dot event file.
Okay, an event file. Why is that so critical?
Because in EEG, event files are like the script or the timing cues. They mark exactly when specific things happen during the recording.
Like when a light flashed, or when the person was told to imagine moving their hand.
Precisely. Without these markers, you just have this continuous stream of brain activity, but you don't know what the person was doing or experiencing at any given moment. It's like watching a movie with no idea what the plot points are.
Okay, so you need the event file, but it was a puzzle.
It was. This specific .event file, its format was a complete mystery. We couldn't find clear documentation for it anywhere for this particular dataset's events.
Uh-oh. So what do you do then? Data forensics.
Pretty much. We tried opening it as plain text, looking at the raw binary data, just hunting for patterns, any clues.
And did you find anything?
We found hints. There was definitely a readable text header at the very beginning, but then it just turned into what looked like, well, binary code.
Gibberish?
Sort of. We started seeing potential patterns, though, like maybe the last 8 bytes of each chunk represented a time and an event ID. It felt like cracking a code, but we didn't have the cipher key. It was pretty frustrating.
I can imagine. So could you actually extract the events using the standard tools?
Well, that was the real problem. We tried using a standard function in MNE-Python, MNE.events from annotations. It's designed for this, but it only found one single event type in the whole file.
T0. Just T0. But your forensic work suggested there should be more.
Exactly. That's what was so confusing. And it really highlights a common challenge in data science. You know, sometimes you get data, but without clear documentation for its specific format, interpreting it correctly is incredibly hard, like having a map in a language you don't speak.
Wow. A map with invisible ink, like you said before. You know there's more there, but you can't quite see it. So that leads us to epoching. The saga. The epoching saga, yes. So to analyze how the brain responds to things, you don't usually look at the whole continuous recording at once. You epoch it.
Epoching. Explain that again.
It's like taking scissors to that long stream of data. You cut out small, precise windows of brain activity centered around each event marker. So if T0 is our event, we cut out a little chunk of data right around time T0.
Okay, like taking snapshots around key moments?
No.
Makes analysis easier.
Exactly. You can average these epochs, compare them. But our first attempt, using that single T0 event, well, it failed.
Failed how?
MNE just reported. All epochs were dropped.
Yeah.
And the error was no data.
No data, even though you loaded the data.
Yeah, it sounds weird. But it meant we were asking for data from a time before the recording actually started. We'd set the start of our epoch window, tmin, to a minute of 0.2 seconds. So 0.2 seconds before T0.
Ah. So if T0 was right at the beginning, you were asking for data from before the recording even began.
Basically how you reference the signal level. The error message actually suggested a fix, set baseline. This means use just the single time point at the event as the baseline, which is fine, sometimes necessary. So we did that.
Okay, progress. Did it work then? Did you get your epoch?
Nope. Still dropped. The single epoch was still dropped.
Oh, come on. Why this time?
This time, the system gave us more detail in the drop log. It listed specific channels, SE5, C5, T7, others saying they exceeded a rejection threshold of 150 microvolts.
150 microvolt. Is that high? What does that mean?
It is quite high for brain signals. That threshold is there to automatically reject epochs contaminated by large artifacts, things that aren't brain activity, like eye blinks or jaw clenches or muscle tension. These create much bigger electrical signals.
So basically, even though you fixed the timing, the data in that specific window on those specific channels was just too noisy, likely due to muscle activity or something.
That's the idea. Our microphones picked up loud non-brain noise right at that T0 moment.
Man, that sounds incredibly frustrating. Fixing one thing, then another pops up. What was the breakthrough? How did you finally get an epoch?
It was a mix of frustration and determination. The detective mode kicks in. The breakthrough was a bit of a compromise, really. We decided to temporarily remove the reject parameter altogether.
You just turned off the noise rejection.
We did, just temporarily.
Yeah.
It meant we were saying, okay, ignore the potential noise for now. Just let us see if we can create this epoch at all.
And
it worked. Finally. We successfully created that one epoch around T0. It was a real yes moment, even knowing we'd have to be careful about the data quality later. Just seeing something was the win.
I bet. After all that troubleshooting, finally getting that window of data. So what did you do with it? What did that first glimpse look like?
We visualized it, plotted the raw signals for that epoch. It was our very first proper look at the brain's electrical activity around T0, seeing those squiggly lines finally appear.
Yeah, that was satisfying. Puzzle piece found.
Okay, so epoching conquered, at least for one event. You have data you can see. Now, the really fun part, bringing it to life, right? Making it visual.
Absolutely. But first, a quick sanity check. We did that channel check comparing the names from our WFDB cal calibration file against the standard 1005 montage map.
Did they match up? Mostly, yes. Lots of common channels. But there were some discrepancies, some differences in naming or maybe placement. Another real-world data thing. Standards are great, but data sets don't always follow them perfectly. You have to double-check.
Always keeping you on your toes.
Yeah.
Okay, channel mapping sorted. Then the big visualization, the aha moment. You mentioned topo map.
Topo maps, yes, they are fantastic. Think of them as 2D maps of the scalp.
Okay.
And colors spread across this map show where the electrical signal is strongest or weakest at one specific instant in time. It's like a heat map of brain activity. Really intuitive.
Cool, so you can see patterns, like maybe activity is strong over the motor area.
Exactly. You can see the spatial distribution, but we didn't stop at just static pictures.
Ah, right, you made it move, the animated brain.
We did. This is a really exciting part. We took a sequence of these top maps, calculated for successive time points within our epoch,
Yeah.
and stitched them together into a GIF animation. We use the ImageO library in Python for that.
So instead of just one snapshot, you get a little movie.
Exactly, a dynamic view. You see the electrical activity changing, shifting, rippling across the scalp map over time. It really gives you a feel for the brain's dynamics. Watching those waves move across the head, it brings the data to life in a way static plots just can't.
That sounds amazing. Seriously, the ultimate payoff after all that detective work. From a misidentified zip file through error messages and weird formats to an actual moving picture of brain activity, that's incredible.
It really felt like it. Makes all the troubleshooting worthwhile. It's that satisfaction of turning complex, messy data into something understandable, even beautiful.
Okay, let's quickly recap this whole journey then. We went deep inside the brain, no surgery needed. We started by finding and downloading that raw EEG data from PhysioNet, the S001RR01.edf file, 64 channels strong.
Yep. Then we pre-processed it, filtering out noise between 1 and 40 hertz to focus on the key brain rhythms. And then we hit the event file mystery, S001R02.adf.event.
The infamous event file, our mysterious friend. It gave us that single teaser event, but stubbornly kept the rest of its secrets hidden because of that undocumented binary format.
Right, which led directly into the epicking saga, wrestling with no data errors, then the rejection thresholds kicking out our data.
Until you finally made that breakthrough by temporarily removing the rejection criteria, just to create that one precious epoch around T0.
Our first window.
No first winner, exactly. And then the visualization finale. Checking the channels, creating those insightful top maps, showing activity across the scalp.
And culminating in that fantastic GIF animation. Stitching the top maps together to watch the brain activity ripple and flow over time, the brain in motion.
From raw file to animated brain map.
It's an amazing process.
Yeah.
But that event file question mark still hangs there, doesn't it? That unsolved piece of the puzzle.
It really does. Without clear documentation for that specific binary format, we can't fully understand all the experimental events. We can't perfectly sync up the brain activity with precisely what the person was doing or imagining. It's a real hurdle. And it highlights something important, right? That data analysis, scientific discovery, it's often an ongoing process. Some puzzles just remain unsolved for now.
Exactly. Maybe waiting for a future deep dive or for someone to find that missing documentation.
So thinking about all this, what does it mean for you listening right now? Consider the incredible potential here. EEG is already used for diagnosing conditions like epilepsy for brain-computer interfaces.
Helping people control prosthetic limbs with thought alone. The applications are growing constantly.
So imagine, if we did have all the pieces to that event file puzzle for this data set and others like it, if we could fully decode these complex brain signals, perfectly aligning them with every thought, every action, every intention, just think. What hidden patterns, what truly profound insights into how our minds work do you think we might finally unlock?
Everything we do is available freely on BioniChaos.com. Please consider supporting me on Patreon, and don't forget to click like, subscribe, and comment. Everything we do is available freely on BioniChaos.com. Please consider supporting me on Patreon, and don't forget to gently click like, subscribe, and comment.
And there is a human in the loop as well. And yes, this data set, we didn't have much luck with it. Well, because we couldn't actually decode the event files. You have this time, a weird time resolution. Maybe we can try it one last time. Can we try decoding, parsing, whatever? And let's see what we get. Probably would not get far. So probably be looking at a different data set next time. We're just unlucky with this one. So just okay, you can run this. So using Colab, Google Colab. It's pretty good. So it's having trouble. It's changing the code. It's having trouble to access the file or something. It shouldn't be a problem. Anyhow, I'll keep trying this in the background. Let's just do overview a different dataset that we will be potentially looking at. Yeah, let's do this one here.
Okay, so ever had that weird moment, right? Where your palms just feel a little sweaty?
Yeah. Even when you're not particularly hot or exercised.
Exactly. Like you're maybe about to give a presentation, or I don't know, you're just brainstorming something cool, and bam, clammy hands.
Right.
Well, it turns out those little beads of sweat, they're not just about cooling you down.
No, not at all.
Our skin, and this is kind of wild, it holds some really surprising secrets about, well, our state of mind.
It really does. It's like this silent billboard, constantly updating.
Yeah, whispering little clues about what's going on inside us. It's fascinating. So today, we're diving headfirst, really digging into this realm where these tiny electrical signals from our skin can actually show us the inner workings of our nervous system.
It's pretty amazing stuff.
Our mission for this deep dive, then, is to unpack what our sweat glands can tell us about our physiological state, especially comparing when we're awake and just, chilling out versus when we're under sedation.
Yeah, two very different states.
It might sound a bit niche at first, maybe a little sci-fi.
A little bit, maybe.
But trust me, the data we're exploring is not only incredibly cool, but actually really relevant to understanding ourselves.
Yeah.
And maybe even the future of health tracking.
Absolutely. And the source material we're using today, it's solid. It comes from a really comprehensive data set published on PhysioNet.
Ah, PhysioNet. Good stuff.
Yeah, for anyone who doesn't know, it's a highly respected open access resource, makes great scientific data available for, well, everyone.
Right.
And this specific data set looks at electrodermal activity, EDA for short, collected really carefully from healthy volunteers.
Okay.
It's foundational work, a real treasure trove that lets researchers all over the world explore and build on what they found.
Okay, EDA. Let's unpack that a bit more. What is electrodermal activity exactly, in simple terms?
Right. So basically, it's a super sensitive way to measure how the electrical conductance of your skin changes over time.
Electrical conductance.
Yeah.
So how easily electricity flows across it.
Precisely. Think of your skin less like just a barrier and more like a dynamic electric circuit board.
Huh.
When your eccrine sweat glands, those are the tiny clear ones all over, but especially dense on your palms and soles when they get active, even a tiny bit, they release moisture. And that moisture, even if it's totally imperceptible to you, changes the skin's electrical properties, how easily that current flows.
So it's not about, visible sweat dripping off you.
Not at all. It's way more subtle. It's a rapid, super sensitive readout of even the tiniest bit of sweat gland activity.
Wow. It's kind of wild how something so microscopic can tell us so much, isn't it?
It is. And what's truly fascinating here is the why. Why is this measurement so significant?
Okay, yeah, tell us why.
Well, the activity of these specific sweat glands, the eccrine ones ED, tracks so well. It's almost exclusively controlled by one part of your nervous system.
Which part?
The sympathetic branch of the autonomic nervous system. That's your body's ancient fight-or-flight response mechanism.
The fight or flight, even when you're just sitting there?
Exactly. Even when you're completely still, maybe reading a book or just zoning out, that system is subtly, constantly working.
Huh.
It's responding to internal thoughts, maybe a fleeting emotion, even tiny physiological shifts you'd never notice.
And EDA picks that up.
It's sensitive enough to capture those tiny dynamic shifts.
Yeah.
It's like having this direct, real-time window
Yeah.
into how your body is reacting and adapting internally and externally.
Without you even consciously knowing it's happening?
Precisely. It's like this quiet internal conversation your body is having, and EDA lets us kind of listen in.
Okay, this is where it gets really interesting for me. Because the researchers, they didn't just look at people doing their normal thing.
No, they were clever about it.
They structured the study to look at EDA in two really distinct states, a direct comparison.
Right.
So first, they had healthy volunteers who were simply awake and at rest, just sitting there.
Okay, the baseline group, essentially.
Yeah. There were 11 people in this group, aged 22 to 34. Actually, they started with 12.
Well, what happened?
Well, they smartly excluded one person because they had something called Raynaud's phenomenon.
Ah, yeah, that affects circulation in the fingers, right? Could mess with the readings.
Exactly. So, good call to ensure the data was clean. These 11 people just sat awake for about an hour, letting their bodies settle.
Got it. Awake and resting.
And then, for the second group, they got a different set of 11 healthy volunteers.
Okay.
But these folks were under controlled sedation.
Ah, okay, now we're talking contrast.
Right. They use propofol, which is a common anesthetic. So you've got one group chilling out, totally conscious, and the other in this completely altered state, deeply sedated.
Wow, what a great way to see how ED changes based purely on consciousness level and, well, nervous system state.
It really is. It's like comparing two totally different worlds inside the body.
So how did they actually measure this? The nuts and bolts of it must have been pretty precise.
Oh, yeah. Super precise and really well thought out. For that awake and at rest group, they put electrodes on the non-dominant hand, specifically index finger and ring finger near the tips.
Makes sense. Lots of sweat glands there.
Exactly. And they used an FDA-approved neurofeedback system.
Sounds fancy. High-tech stuff.
Yeah, sounds it. But basically, it's just a very accurate tool for measuring these subtle electrical changes.
And how long did they measure for?
About an hour. And get this, they collected data at 256 hertz.
256 readings per second.
Yep. Crazy, right?
Wow. That's a ton of data.
It is. And the subjects, they could read, meditate, watch something on a laptop. But crucial detail, they couldn't write with the hand that had the sensors on it.
To avoid movement artifacts, presumably?
Probably. And importantly, it was purely observational. They didn't zap them with stimuli or anything.
Right.
And didn't control what they read or watched. Just natural, spontaneous EDA.
Okay, so that's the awake group. What about the sedation group? Must have been different.
Yeah, a bit different, more clinical setting, as you'd expect. Electrodes went on the palm of the left hand.
Palm? Oh. Also dense with glands.
And they used an FDA-approved bedmaster system, something you'd typically see in hospitals.
Right, for patient monitoring. Makes sense.
Data collection here was much longer, about 3 to 4 hours.
Longer period, okay.
And an even higher sample rate, 500 hertz.
Ooh. 500 readings a second.
Plus, during that time, the propofol concentration was actually changed. Varied over time.
So they could see the effects at different depths of sedation. Very clever.
And it's really crucial to mention the ethics here.
Absolutely. Always important.
Both parts had full IRB approval, that's the ethics board, from big names like MIT and Mass General Hospital.
Top institutions. Good.
And of course, everyone gave written informed consent, everything done responsibly and ethically.
Excellent. That's foundational for this kind of human research.
So, okay, all this incredibly careful data collection, what did they actually find? They didn't just end up with, like, messy, squiggly lines, right?
No, definitely not. They took that raw EDA data, all those hundreds of readings per second, and they processed it. They extracted two key things, the real nuggets of knowledge here.
What were they?
Pulse times and pulse amplitudes.
Pulse times and amplitudes. Sounds like finding the peaks in the signal.
Kind of like that, yeah. Think of it like finding the distinct moments of activity, the pulses, and how strong each pulse was. These specific little electrical wiggles, that's the gold. That's the key to understanding the nervous system activity.
Right. So the big question then, what did these pulses, these little wiggles, actually show? What was the difference between the awake folks and the sedated folks?
Exactly. And this is where it gets really cool, because the data just spoke volumes. By looking at those pulse times and amplitudes, they saw some really clear, profound differences between the two groups. It was quite striking.
Okay, tell me more.
So, in the awake resting group, they saw this consistent, dynamic baseline level of spontaneous EDA fluctuations, little ups and downs.
Even though they were just sitting there resting.
Yep. These weren't necessarily tied to anything obvious happening outside. They were subtle, continuous shifts. It showed that constant low-level buzz of the sympathetic nervous system.
Always kind of active in the background.
Exactly. The pulses were, relatively frequent, but their amplitude, how strong they were, that varied quite a bit. It's like the nervous system was just gently processing internal stuff, thoughts, feelings, who knows.
Okay, so a kind of gentle buzzing baseline for awake people. What about the sedated group?
Ah, well, that's where the contrast was huge. In the sedated group, those spontaneous ED fluctuations were significantly suppressed. Often the line was much, much flatter.
Really quieted right down.
Massively. The pulse times became way less frequent, fewer bursts of activity. And the pulse amplitudes, the strength of those bursts, were dramatically reduced, sometimes almost gone, especially when the propofol level was higher.
Yeah.
It showed this really clear quieting of that spontaneous sympathetic nervous system activity, like switching it way down.
So it's a direct reflection of consciousness level impacting those automatic responses.
That's exactly what it suggests. This clear difference between the states, it's a crucial insight. Being awake means your nervous system is always subtly reacting, processing, even subconsciously.
Right.
While sedation really dampens that automatic reactivity way down, it really highlights EDA as a potentially powerful biomarker for your physiological state.
That is a profound difference. Okay, so suddenly this seemingly technical data feels incredibly relevant, like relevant to me,
Absolutely.
Because findings like these, they fuel that growing interest in using EDA to track physiological conditions like stress, sleep quality, emotions.
Exactly. Imagine a future, and maybe it's not that far off, where a simple sensor, maybe on your watch or a ring, could give you real data on how rested you actually are, or if your stress is creeping up, just by reading these silent whispers from your sweat glands.
That's amazing. Not just guessing based on how you feel, but
Yeah.
getting actual biofeedback.
Precisely. It moves beyond subjective feelings into objective data. It's not just abstract lab science anymore. It's about unlocking really personal insights.
Yeah, it feels less sci-fi now and more like applied science that could genuinely help people.
And that links back to why sharing this data on PhysiNet is so important.
Right, making it public.
Yeah, the whole point is to empower other researchers. Let them explore this phasic EDA data, understand the rich information it contains.
So everyone can build on it.
Exactly. It
Yeah.
accelerates discovery. People can test new ideas, develop new ways to analyze it. It helps build better computational models for autonomic nervous system activity.
And has it already been used like that? Has it led to new things?
Oh, definitely. This data set has been instrumental in developing a new physiology-driven framework for ED analysis, something called a point process framework.
Okay, sounds technical, but the point is the data is useful.
Hugely useful. It shows how these foundational data sets are just critical building blocks for making big scientific leaps in understanding the body.
It's amazing how one careful study can ripple outwards like that.
It really is.
Mm.
Of course, like any study, you have to consider its context.
Sure. Limitations.
Well, for the at-rest awake group, remember it was purely observational.
Right, no specific triggers applied by the research.
Exactly. They were just watching what naturally happened, which is valuable in itself, but it's different from a study where you apply specific controlled stimuli. It just provides context for interpretation.
Got it. Doesn't diminish the findings, just frames them correctly. Okay, so, wow, we've taken quite the journey here into these tiny, almost invisible electrical changes on our skin.
We really have, from just chilling out awake to being completely sedated.
And what we found is that these subtle shifts, these electrical whispers, they give us genuinely crucial insights into our fight or flight system, our overall physiological state.
Yeah, it's pretty remarkable.
It just really drives home how even simple measurements, if you do them carefully and analyze them smartly, can unlock this complex, utterly fascinating picture of the human body.
Mm-hmm. It's constantly talking, isn't it?
Our bodies are always communicating. We just need to learn how to listen.
Right. And, this whole thing, it raises a really interesting, kind of provocative question for me.
Oh, yeah. What's that?
Well, if our skin can silently broadcast so much about our internal state, our alertness, our stress responses, even our level of consciousness, what other hidden signals might our bodies be sending out all the time? Signals that we're only just beginning to figure out how to decipher.
That's a big question. Like, what else are we missing?
Exactly. Think about how insights from seemingly simple data, like this sweat data today, could genuinely revolutionize how we track stress or sleep or emotional balance in the future.
Giving us that clearer, more objective picture you mentioned.
Yeah, without us even needing to say a word about how we feel. It really makes you wonder, doesn't it? What else are our bodies secretly telling us, just waiting for us to tune in?
Everything we do is available freely on BioniChaos.com. Please consider supporting me on Patreon, and don't forget to click like, subscribe, and comment. Everything we do is available freely on BioniChaos.com. Please consider supporting me on Patreon, and don't forget to gently click like, subscribe, and comment.